Welcome to HCH32. Tutorial 1. Machine Learning Training Scale-Out.
An input to this layer in a forward pass, so that's the yellow matrix X. Now, so this tells us how to update this layer later on, but now we also need to send the gradients backwards to the preceding layer, and that's where the activation gradient computation comes in. So here you again take the gradients that are flowing back, dy, multiply them with the layer's weights, and produce the gradient to be fed into the preceding yellow layer. So finally, we'll get to the weight update portion, where we will take the gradients that we just computed, so the hashed purple matrix, and the weights at this particular point in time, so the solid purple matrix, and combine them pointwise to produce the updated weights. And we'll keep repeating this process, then we'll run the next forward pass and so forth. So for the optimizer, well, which performs the weight update, the inputs are the current network weights, also the weight gradients that we just computed in the backward pass, and the output is updated weights. Operation is some pointwise combination of the two. It will really depend on the particular optimizer math, but it's also important to realize that it may have internal state, which is another one or two matrices of the same size, often called momenta. So on the right-hand side here, you'll see SGD, so that's stochastic gradient descent. We just combine the gradient multiplied with the learning rate with the weights and produce new weights. If you have, let's say, SGD with momentum, now in green we have one of the momentum matrices. Again, they have the same size as the weights. So first you update the momentum, then you update the weights, and you continue training. So to summarize all the compute that happens during training for one given layer, we have the forward pass, which ends up being a matrix-matrix multiply. We have a backward pass made up of the gradient computation for activations and weights. So effectively, very roughly, we can say that backward pass has twice the compute of the forward pass. And then we have the weight update, which is some pointwise combination of several matrices. Now, an important thing to note is that you do have to keep the activations from the forward pass, so the yellow matrix here, X, which we receive as input on the forward pass, you do have to retain it for computation in the backward pass, as we see in the second sort of matrix equation here, to compute the weight gradients. And this leads to quite a bit of memory being required to train these neural networks, because the deeper the network you have and the wider it is, the more activation space will be required. So a quick example is ResNet 50. If you train that in half precision at batch size 256, you need about 15 gigabytes of memory, and about 12 gigabytes of that memory are actually activations that are being kept from the forward pass to the backward pass. There are some tricks you can play to reduce that by gradient checkpointing and so forth, but it's an important thing to notice, and it's one of the factors that requires scale out, just to have more memory overall for training. Okay, so we just looked at the summary of all the computation required for training of a single layer, and the same thing happens for every layer in your network. So to help cope with all of this compute that's required, as well as memory amount that's required, training at scale is a solution. That way you get more memory and you get more compute horsepower. So a quick view at the taxonomy of various ways to train neural networks in parallel, right? So we have parallel or distributed training, and at the highest level you have a choice of data parallel versus model parallel training, and then model parallel has two subvariants that we'll look at in more detail. So let's start with data parallel, which is the most popular way to train at scale nowadays. So in data parallel training, each worker has the entire copy of the neural network model. So it has all the parameters. They're replicated on every single worker. And what workers partition or parallelize is each of the training mini batches gets sort of split up across all the workers. So data is sort of handled in parallel, and the models are just replicated. So in a forward pass, each worker will take its portion of the incoming data, process it for the layer, produce its portion of the output mini batch. And actually, I think it's easier to illustrate with a diagram. So here, let's say we have a system with just 4 workers. Those are sort of spread out vertically. And we see that each worker has a copy of the entire matrix W, so all the weights for this particular layer, so the purple matrix. However, the input activations X, which would be an 8x8 matrix, in this case are partitioned across the 4 workers. So each worker gets its own 2 columns of the incoming activations. And sometimes you'll see these shown as activations multiplied with the weights. The idea is exactly the same no matter which way you write out linear algebra here. And then because of the way these vectors are set up, so whatever's grayed out, that particular worker does not have a copy of. So then each worker produces a fraction of the output matrix, but it produces complete values for those vectors that it outputs. So we'll see worker 0 produces sort of the light purple portion of the output, and worker 3 produces the darkest portion of the output. No communication is needed in the forward pass because the output that a given layer produces or a given worker produces becomes its input for the next layer, right? So we produce, for example, for worker 0, the first 2 columns of the output matrix, but that's all the columns of that matrix that we need to process the next layer, so we do not have to communicate. And backward gradient computation is essentially the same, so we will not illustrate it, but it is interesting to look at the backward pass and computing the weight gradients. So here, we are multiplying activations with activation gradients. So gradients are dy, activations that are kept from the forward pass are x. They're transposed, so it's the same data that the worker produced or received as input in the forward pass. But now we'll see that each worker produces what looks like the full activation gradient matrix, weight gradient matrix dw. But those are shown in different hashings to indicate that these are really just partial sums. So if you think about a single dot product, for example, in math, each of the workers really just has, let's say in this case, a quarter of each input vector. So the result that you produce is really a partial sum. To produce the overall gradient, you have to sum up all of these contributions together. So all the workers will have to communicate with each other in order to sum up their contributions to dw. At that point, they all have the same gradient, and then they have to be, then you can do model update. So as I mentioned, communication-wise, the pattern that you encounter is called all reduce. So there's a lot of borrowing of terminology from message passing interface, or MPI. Effectively, every worker has to sum up its values with everybody else's values, and then they all have the same copy at the end. After all reduce, each worker has the same exact global gradient. Now that gradient has contributions from all the samples in the mini batch. Therefore, each worker can do a local update of the model. And since they all started with the same model, they do the same update with the same gradients at this point. They end up again with an identical model replicated across all the workers. Now, we are introducing communication, and all reduce is not a cheap communication. So all of the communication is overhead compared to, let's say, training sequentially. Therefore, it is important to do this communication as efficiently as possible. So you want to use efficient communication patterns, efficient hardware and software for communication, and also try to overlap communication with computation. There are several implementation choices for all reduce, but effectively all the bandwidth optimal ones divide up the work across the n workers. So if we have n workers, the idea is that each worker is going to be responsible for summing up a fraction, 1/nth of all the weight gradients. So it will receive them from n-1 peers in some number of steps, sum them up, and then it also has to take its sum, so its fraction of now full gradients, and distribute them to all the n-1 peers again. Quick look at a couple of algorithm implementation ideas. So there's ring reduction. It's designed for any topology that contains a ring. So in this particular case, each worker communicates with 2 of its peers. So let's say neighbor to the left, neighbor to the right. And you will have 2 times n-1 steps. And in each step, the worker receives some data from neighbor, let's say on the left, carries out some operation, and passes on the result to the neighbor on the right. As a result of that, you effectively have 2 to the n-1 synchronization steps in this communication pattern. Some of that can be overlapped with pipelining and so forth. An alternative is one-shot reduction, where now you are assuming that you have a fully connected topology underneath. So each worker is communicating with all of its peers. So you can assume that they have a direct connection, which you can assume whenever you have, for example, a switch in your hardware for communication. So now each worker will communicate with all the n-1 pairs. It will read their fraction of the gradients that they computed, sum it up, and then scatter it back out to them. So you effectively end up with 2 steps, even though each step has n-1 substeps. But you only need to synchronize once per step. So you only have 2 synchronizations versus 2 to the or 2 times n-1 synchronizations for the ring reduction. So that does help with some of the overheads involved in training at scale. And it also allows you to take advantage of switches if they can do arithmetic. So for example, Mellanox switches that have sharp capability, they can do some in the switch hardware. So again, you can offload some of this computation from the accelerator that would do math typically. Now, part of the all-reduced math is actually being carried out by networking hardware, freeing up the accelerators to carry out computations. So quick note on communication implementation, because at first glance it might seem pretty simple. It's all reduce, you just go through steps, carry out sort of pretty simple patterns. But underneath there are many implementation details that do matter. Because accelerators or processors that carry out the math for deep learning training, they have multiple communication ports. Right? If we look at a few, say, NVIDIA systems, so Volta GPUs had 6 communication ports for NVLink. Ampere GPUs, the latest ones, have 12. Now, each of those ports is also bidirectional. So now you effectively have to have twice the logical communication channels to really saturate your networking hardware. And finally, you will use pipelining to hide synchronization latency or startup of communication and wind down. So what that effectively means that, for example, looking at the DGX1 system, you have 6 NVLinks. Therefore, you end up with 6 rings just from that. So in the particular diagram, the various shades of green and gray sort of bidirectional arrows correspond to the logical rings that you have. But you have a ring in each direction. So really the communication library will utilize multiples of 12 rings to execute a single all-reduce. If we look at the NVIDIA DGX A100, the system has 8 GPUs, but they have 12 NVLink ports. Again, they're duplex. But now they're connected to a switch. So in this case, communication library like NCCL, which is NVIDIA Collective Communications Library, it will use multiples of 24 rings or one-shot instances to carry out an all-reduce. So there's quite a bit of an orchestration that has to happen behind the scenes. Okay, communication overlap is also pretty important. So you may have noticed that when we do the backward propagation, we have a pipeline actually happening, right? So one layer computes the output or its gradients, sends them to the preceding layer. That layer repeats the computation, passes it on to the preceding layer, and so forth. So you can actually overlap computation for layer k with all reduce happening for layer k plus 1. So in this figure, we could be computing the gradients for layer 2, so the purple layer, and at the same time, we could be all reducing the gradients that were produced by layer 3 or the blue layer, because now the data flow is backwards. So in this fashion, you can sort of reduce the exposed overhead of communication. You cannot completely hide it because layer 1, the very first layer, its gradient reduction cannot be overlapped with any computation. At this point, we've run out of pipeline stages. Also, communication and computation will compete for some of the same resources. They'll compete for memory bandwidth of a particular processor, and if the processor is also carrying out the reduction, they'll compute for math pipelines as well, and math resources such as registers and so on. So that's why, again, offloading some of the reduction math to the switches is quite appealing because you free up more time for the accelerators to carry out the backward math, computing the activation and the weight gradients. One last detail to consider for data parallel is distributed optimizer. So as we have seen, in data parallel, each worker does 1/nth of the work for the forward and backward propagation. So that work gets reduced by a factor of n whenever you have n workers. However, after the gradient reduction, each worker traditionally would update all of its model parameters. So no matter how many workers you have, each one goes through the entire model and carries out weight optimization or weight update. So that amount of work does not scale down with the system scale. And at larger scales, that can lead to weight update dominating that time. Right? If you go to 1,000, 2,000, or 4,000 workers, now each one is doing, let's say, 1/4,000th of the work to do the forward and backward pass, but still does 100% of the weight update. So the solution to that is distributed optimizer. Effectively, what it does is inserts weight update in the all reduce stages. So if we look at the 3 steps of all reduce, a worker has to collect gradient contributions from all of its peers. That's the same as before. But now, typically the worker would do the update of everything locally and then distribute it to its peers. Here, it updates only a fraction of the weights. So each worker is responsible, let's say in a 4-worker system, for 1/4 of the weight update. It carries out that work and then distributes the work back to the peers. So this way you actually scale the weight update work also by the factor of n on an n worker system. And this has appeared, to the best of my knowledge, for the first time in MLPerf v.6 submissions. I think it was for Transformer Network. TPU system used that. And then later Microsoft Zero paper also described various variants of this approach. Okay, so data parallel sounds great. A lot of systems use it nowadays, but it does have a few challenges. And those can be sort of grouped by parallelism type or scaling type. So strong scaling, whenever you take your workload and keep the workload constant but keep increasing the number of workers. So in our case, we would keep the mini batch size constant but use more and more workers, would constitute strong scaling. That will create a couple of challenges. One of them is that certain layers, well, one thing that will happen is each worker will get smaller and smaller mini batch or sub-mini batch as you scale out the system, right? Because the overall global batch size is fixed. Certain layers, such as batch norm or batch normalization, require a minimum number of samples to operate properly. So as a very rough rule of thumb, batch normalization requires 16 or more samples to operate properly. Otherwise, networks tend to blow up and not achieve good results. So as soon as per worker sub-mini batch goes below size 16, you need additional communication in both the forward and the backward pass just to maintain the functionality of training. These will effectively result some all reduces, but only within groups, small subgroups of workers at a time. Another aspect of scale or of strong scaling is that as each worker gets smaller and smaller sub-mini batch, it may become less efficient at carrying out that math, right? So we started out with matrix-matrix multiply, but then as you use more workers, the activations are going to become sort of a skinnier and skinnier matrix, ultimately potentially becoming just a single vector. So that brings us to weak scaling, where you increase the mini batch size, that's the workload, along with the number of workers. That also comes with its own challenges, and they're more application side in this point. So some networks will require hyperparameter adjustment whenever you train with large mini batches. So such as learning rate schedule, even the optimizer itself, again, batch normalization parameters have to be adjusted to keep achieving the same quality of the network at the end, to achieve the same accuracy. One example of that is ResNet 50, where if you use stochastic gradient descent, you can just use SGD with momentum for up to batch sizes of 16,000 images. However, if you go above 16,000 images in a mini batch, then you have to switch the optimizer to Lars and tweak some other hyperparameters. Another thing that happens with weak scaling is that as you train on larger mini batches, you actually require more work to achieve the same accuracy in the network. So it's useful to look at some results from MLPerf. This is from MLPerf v.7, which just concluded a couple of months ago. So looking at two networks, ResNet 50 and GNMT. One is an image network, one is a language translation network. And on the x-axis, we have mini batch size in thousands of samples. So either thousands of images or thousands of sequences to be translated. And on the y-axis, we have epochs. So the number of times you have to traverse the entire data set during the training process. So we'll see that for the smaller mini batch sizes, the various submissions sort of cluster at fewer epochs. For ResNet 50, if your batch size is somewhere between 2,000 and 8,000 images per mini batch, you'll see that we need 40 to 50 epochs to reach target accuracy. If we go to the other extreme, where we are using batch sizes of 64,000 images or greater, you will see that we take more than twice the epochs to achieve the same accuracy in the network, so around 90 epochs. Right, so by going to larger batch sizes, we can still successfully train the network, but we just have to do more work to get there. Something very similar happens to GMT. So at batch size 2,000, you require about 40 epochs to train it to accuracy. At batch size 16,000, so 4 times bigger batch, you'll require twice as many epochs, so twice as much work to achieve the same accuracy. And this is one of the issues that large systems have to contend with. They do have to do more work to reach the target accuracy, but the idea is that as you scale out, the increased workload is still smaller than the increase in performance, so it's still a net win. Okay, so that was data parallel. The alternative to data parallel is model parallel. So whenever you get to a point where, for example, you can no longer reach accuracy at a larger batch size, or you've exhausted data parallelism, then the only option you have is model parallel. And the idea for model parallel is just the opposite of data parallel. So rather than partitioning the data or mini batch across workers, you are actually partitioning network parameters. And each one also gets some subset of the data. So as we mentioned at the beginning, there are two variants, interlayer parallel or pipeline parallel. So that's the one at the top, where effectively you will take your set of layers in a network and partition the layers across the workers. So worker 0 gets a set of layers, in this case layer 1 and layer 2. Worker 1 gets some layers, and worker 2, in this case, just gets a single layer. And they each will be responsible for just doing the math for their layers and nothing else. The alternative is intra-layer parallel, so that's the bottom example here. In this case, each worker gets a fraction of every layer in the network. So worker 0 gets sort of the quote-unquote top portions of each layer, worker 1 gets the middle one, and worker 2 gets the bottom one. And we'll have more detailed examples coming up. So let's start with pipeline parallel approach. So in this case, we have 3 workers, and the first 2 workers get 2 layers each, and they're contiguous layers, so layers that appear in sequence, and the last worker just gets 1 layer. And in this case, horizontally, we have time flowing, so effectively steps that are taken to execute a single mini batch training step. So the activations going in the forward pass are shown as a blue matrix here, and the sort of purple bars indicate sort of delineation between different steps. So in the very first step, worker 0 gets the input, passes it through its first 2 layers, produces an output. It then communicates that output to worker 1. Worker 1 now gets the output from the first layer, which is its input, sends it through 2 of its layers, produces the output, sends it to worker 2. Worker 2 will take what it received, pass those activations through its layer math, and then compute the loss. Now that we have the loss, we can start the back propagation, and it just happens sort of in the opposite direction. So worker 2 now will compute the gradients for its layer. Then, as it has those activation gradients, again shown as sort of hashed blue matrix now to indicate that it's not activations anymore, it'll pass it back to worker 1. That will go through the same steps. It takes the incoming activation gradients, passes them through 2 of its layers. Whatever it produced passes on to the first worker, or worker 0, which will do the same work. So this actually is a pretty poor example of a pipeline because at any given point in time, we only have a single worker doing any computation. So for 2/3 of the time, for 12 sort of step slots that we have in this diagram, we were idling. But as is typical to any pipeline, you really want to take all of your workload and partition into smaller chunks. That way they can flow through the pipeline overlapping with each other. So it's a classical pipeline idea, right? So in this particular case, we'll take the input matrix and we split it in half. So I still show the matrix in its entirety here, but only 1/2 is blue. So that's the data that we have at the moment. And the portion that's white, it's really not there, but it's sort of to indicate that this is the full matrix that we're processing. So now we take twice as many steps to achieve the same work, but each step is also half the amount of work, right? Because at each point, we're just working on half of that matrix, just the blue portion that's filled out. So if we go through time, now we have improved the efficiency of our system. In this particular case, we only idle for 50% of the step slots, which is an improvement of over 67% in the previous slide. And in the limit, as the number of workers grows, if you have the same number of sub-mini batches as the number of workers, so K in this particular case is sub-mini batches. So if number of workers is also equal to the number of pieces of the mini batch to be sent through the pipeline, then you're asymptotically approaching about using your system at 50% efficiency because half the time you'll idle. And you can address that problem by taking your input matrix, the activations, and breaking into finer and finer pieces by increasing the K. So if K is, for example, 4 times the number of workers. So let's say if we have 1,000 workers, but we'll take our mini batch and divide it into 4,000 sub-mini batches. Then we use our pipeline more efficiently. We're effectively making the pipeline deeper and therefore maximize the overlap. So in that case, you would asymptotically approach idling only 20% of the time. So that sounds pretty good. There's an additional trick to keep workers more occupied, is if we look in the slide that we just examined, here each worker gets a contiguous sequence of layers. So on the very left, try to move the mouse. So when we look at the neural network here, the little diagram, worker 0 gets layer 1 and 2, worker 1 gets layers 3 and 4, and so forth. That is nice because as it's processing information for its layers, it doesn't really have to communicate. It only has to communicate on the boundaries of its layers when it has to pass information to the next worker. But all the work internally is completely local, no communication. If we take the alternative approach, where now each worker still gets the same amount of layers, but they're no longer contiguous. So in this case, worker 0 gets layer 1, and if we look down, worker 0 also gets layer 4. And again, worker 1 also gets 2 layers in this fashion, but they're no longer layers that appear in sequence. We actually utilize the pipeline more efficiently. For example, if we look at worker 0, previously it was idling 50% of the time, but in this case, we have a total of 6 steps in the forward pass, but worker 0 is busy for 4 of them. And the only cost for this is actually we have more frequent communication, because now we have to communicate after every single layer. And also topology has to change from, let's say, a 1D mesh to a 1D torus, because what's going to happen if we look, for example, at processing a particular sub-mini batch. So let's say the very first one where only the left part is filled in blue. So worker 0 will process it, then it communicates it to worker 1. Worker 1 processes it, communicates it to worker 2. Now worker 2 has to pass it on to layer 4, which is owned again by layer 0. So you have another communication. So worker 2 also has to have a connection to worker 0, effectively a wraparound connection. So that's how you end up with a torus topology logically. There are some downsides to this approach. So it does increase communication linearly. As sort of you reduce the number of layers that a worker owns that are in sequence, by the same factor, you'll be increasing the amount of communication that will happen on your network. Also, this pattern breaks down and cannot be applied whenever you have skip connections in your neural networks. So let's say if your neural network here, it's a very simple network where information just flows linearly from layer to layer. But for example, if we had a skip connection also from layer 1 to layer 3, this would really make communication much more complex. It can still be implemented, but the complexity really sort of gets to the diminishing returns point to where it's often just not worthwhile. So downsides is more communication and also complexities when implementing some networks. And skip connections are actually pretty popular nowadays. You'll see in some subsequent talks today when looking at transformer and other language models, they do have skip connections. Okay, so communication that's involved with pipeline parallel. In this case, a worker communicates only with 2 of its neighbors. So 1D mesh topology is sufficient. You need a 1D torus if you use sort of the layer interleaving approach. Communication now is needed in both the forward and backward passes after each layer. To contrast that with data parallel, we just needed communication before the weight update. And in this particular case, communication is very hard to overlap with computation. And the reason for that is, if we look at the simplified diagram here, is that a worker can't really start doing its work until it received all the inputs from the preceding layer or from another worker. So worker 1 can't really start working until it received all of its input from worker 0. So we can't really overlap that communication with some kind of computation if we're still doing synchronous weight updates. In some cases you can, but it gets very, very involved. Okay, so looking at the pipeline parallel challenges, so as we mentioned, there's lots of communication. Communication is hard to hide, and any communication that's exposed really becomes overhead and reduces your scaling efficiency. Pipeline parallel, as we've seen, also introduces this concept of idle slots or idle time slots, as any pipeline computation would. And again, those idle time slots will decrease your scaling efficiency. Right? So you have to have deeper and deeper pipelines to reduce the idling, but that results in more and more communication. So it's sort of trade-offs that really fight against each other. A third challenge of pipeline parallel is load balancing. We looked at the networks where, let's say, here, each layer was doing the same amount of work, but many modern networks, especially in image domain, they have a sequence of layers that are very different in their nature, and they do different amounts of computation. So at that point, it's really hard to ensure that each worker's time slot is of equal length. And whenever they're not, effectively you're dealing with a pipeline where stages are not taking equal amount of time. Therefore, effectively, because of synchronizations, all the pipeline stages really will take the same amount of time, except that a number of workers will idle even within their own stage when they, in theory, did have some work. So all of these issues sort of combine, making pipeline parallel pretty challenging, so it's not widely used today as these issues are being worked through. Now, model parallel, by taking the intra-layer parallelism, tries to address some of the challenges of pipeline parallel. And effectively, well, as we will see, it still has lots of communication, and that communication is hard to overlap, but it does address idle slots by effectively eliminating them, and it also addresses load balancing by effectively eliminating that issue. So whenever people train with model parallel approaches nowadays, they're usually intra-layer parallel. And intra-layer meaning is that within a single layer, you have parallelism by distributing that layer across different workers. So two variants of intra-layer, effectively defined by how you partition the weights of the particular layer. So we'll look at the case where your weights are just a matrix, a projection matrix, so that's the yellow square matrices at the bottom here. And the variants are row-wise partitioning and column-wise partitioning. So those do exactly what the name suggests. Row-wise partitioning will take your weight matrix, that partition its rows across the workers, and column-wise will partition the columns of that weight matrix across workers, and then proceed with computations. So let's take a look at illustrations of those. So this is row-wise partitioning. So what we have here, for example, looking at layer K. So I'll try to use the mouse. So this block of operations here on the very left, we have 3 workers. Each one gets a third of the rows of the weight matrix. So those are in yellow. So that was grayed out, that worker does not have. So we are distributing model across the workers. The blue matrix, the blue skinny matrix, represents input activations. So you have to multiply the weights with the activations to produce the outputs. And the outputs in this case are green. I tried to be clever, combining yellow and blue results green. So in this particular case, we'll see that each worker takes its fraction of the weights, multiplies with all of the input activations. So you'll see that input activations, the blue matrices, they are replicated across all the workers. But after that multiply, you produce only a third or a fraction of the output vector or output matrix. So the first worker produces the first third of the output matrix, second worker produces the middle third of the output matrix, and so on. Now, if we look at layer K+1, sort of skipping the communication phase briefly, we see that all the workers, they need all of the activations that were produced by preceding layer. So you don't just take a third that you produced yourself, you need all of them. Right? So this is where the difference with data parallel comes up, because in data parallel, you only needed the portion of the output that you produced yourself. Now you need every peer's portion as well. So this creates the need for communication. So that's the middle stage here, sort of highlighted in purple. And the communication pattern is all gather. So there's no math in this particular case, but now each worker has to go and gather up the fractions of output that all of its peers produced. And then it can proceed with the next iteration, doing the same computation again and again. Column-wise partitioning does just the opposite. So now each worker here gets a third of the columns of the weight matrix. So those are shown in yellow here on the very left. And now you'll see that the blue, which is the input activations, we no longer have all of those activations. We have only a portion of them that are needed here. So worker 0 will take its fraction of yellow columns. They'll take its fraction of blue rows, multiply those together, and produce the green output activation matrix. Now, actually, I'm not sure how well that's carrying through, but you'll notice that each worker produces a slightly different green matrix. They are hashed in different patterns. And the reason for that is that while they produce a full size activation matrix, they use different values to produce them. So to really create a vector for the, or matrix for the output, you have to sum all of those matrices up. And that's where the communication happens in between. And again, it's needed because the next layer, layer k plus 1, again, it needs only a fraction for each worker of the input activation, but that input activation must have had contributions from all the workers. Right, so that's why the reduction happens. So the pattern communication-wise here is reduce scatter, again, borrowing MPI terminology. Effectively what happens, so each worker, when you see the plus sign here, it gets the corresponding fraction of output activations from all the peers. So we'll just look at, let's say, worker 0. Worker 0 has to produce the complete third of the output. So it looks at the third that it computed, but it also looks at the top third that worker 1 produced and the top third that worker 2 produced, sums them all up, and now that becomes its input for the next layer. And all the other peers do the same. That's effectively column-wise partitioning. Now, what's going to happen here for both of them is whenever you have these sort of purple communication phases, whether they're all gather or reduce scatter, you will have synchronization effectively across all the workers because you have to collect data from all of your peers. So they all have to complete computation, synchronize, communicate, and only then proceed to the next stage. So that's, again, where lots of communication comes up because you need it after every single layer. There's a way to synchronize or to reduce the amount of synchronization by alternating how you partition your layers. So in this case, we kind of combine the two examples, and we have 3 workers as before. And the first one does row-wise partitioning. So you'll see its yellow matrix is partitioned in rows. And we've seen how this operates 2 slides ago. Then let's say after that, the next layer is really partitioned by columns. And one observation to make here is that now in this situation, the output produced by worker 0, the green, top green third of the output, is really all that is needed as input for the next layer. So you avoid communication in this particular case. You will need communication afterwards, as we'll see in the next slide. But the idea here is now you have the number of synchronizations that are needed, which is a nice benefit. So here I've also added another layer. So effectively by interleaving these partitionings, you will have row-wise partitioned layer, column-wise partitioned layer, row-wise layer, column-wise layer, and so on. And the idea is now you'll only have communications after a pair of layers rather than after every single layer. Now, communication is a bit more expensive because you will need an all-reduce pattern. So again, the pair of layers process their data, and for layer k plus 1, the one that's column partitioned, it produces what looks like a full-size activation matrix dimension-wise, but it doesn't have contributions from all the training samples. And then the next row partition layer needs all of the green matrix contributions. So again, you take all the partial contributions that were computed by all the workers, they have to get summed up, and then you can proceed to the next stage. So that's where you get with get the all reduced pattern. And actually, if you remember at the beginning, we mentioned that you can do that on a ring or you can do it with a switch. So this actually is a pretty good illustration of how one-shot all reduce operation takes place. So if we look at the worker 0 in the communication phase here, what it's really doing, it's collecting the top thirds from itself and all of its peers and summing them up. So that's the first step in in one-shot reduction. You get some corresponding fraction of data from all your peers, sum it up. And then in the second step, you broadcast it out to all your peers. And that's exactly what happens after the summations. You take that top third of the now complete matrix, you keep it for yourself, but you also broadcast it to every peer. And all of them do the same thing, just on a different fraction of the matrix. So that's how after all reduce, you end up with a full output matrix on every single worker, and therefore you can repeat this pattern of layer pairs again. Okay, so intra-layer parallel communication for it is actually kind of interesting. We don't have much time, so I'll just sort of leave it maybe as an exercise to you. But row-wise partitioning on a forward pass if you used it in the forward pass, it becomes actually column-wise partitioning in the backward pass, and vice versa. So now, if we look at the communication patterns, if you use row-wise partitioning in the forward pass, you use all gather. On a backward pass, you would use reduce scatter. And we've seen illustrations of both of these. Column-wise approach does just the opposite. In a forward pass, it carries out reduce scatter communication pattern. In a backward pass, it will do all gather. Right, so they're kind of like conjugates of each other. And we'll see how that's used, for example, for Megatron training later on today. And when you combine row and column parallelism and sort of alternate them in pairs, then in both forward pass and backward pass, you end up with an all-reduced communication. The amount of bytes you ship around is likely the same as in either one of the choices above, but you do have half the synchronizations, which is always a good thing at scale, because as you scale out to thousands of workers, synchronizations get expensive, and they do add to substantial overhead. So reducing synchronizations is always a great benefit to keep your training more efficient. Okay, so a quick summary of communication patterns that get encountered. So if we looked at data parallel training, the communication pattern was all reduce of the weights, and it can be overlapped with computation. If we look at pipeline parallel, your communication is pointwise. You're just communicating with two peers of yours, but communication is of activations and activation gradients. It is hard to overlap with computation, and it is also hard to load balance. Next, we have intra-layer parallel, and that has all gather and reduce scatter communication patterns. And I guess what it's communicating are activations and activation gradients, right, as opposed to weights for data parallel. It could be all reduce if you use alternating parallelisms, and it also is hard to overlap with computation because you're just dealing with this idea that one layer computes another layer's one layer's output is another layer's input, and if they live on different workers, communication has to complete before the next one can start its work. What we did not show diagram for is hybrid parallel, where you can combine data parallelism with model parallelism. So this is actually pretty common for recommendation networks, where your embedding matrices are very large. So they can be up to terabytes in size. So those are really handled in a model parallel way. You take your embedding, you spread it across various processors or workers, and each one will do lookup for all over the mini batch, and then the MLP portion of, or the fully connected portion of the recommended network is being executed in a data parallel fashion. So in between, you end up with an all-to-all communication pattern, which basically means that each pair of workers is exchanging a unique set of values. So for this communication pattern, really the switch topology or fully connected topology is optimal. You can carry it out on any topology, but then you'll have some extra steps and redundant utilization of or sends over the same links. That too is hard to overlap because the workers that produce the outputs that become inputs to the other workers after you switch parallelism, you can't, the workers cannot really start any computation until they receive all of their inputs. So as a standard with any kind of like model parallel fashion, it's hard to do overlap of compute and communication. There are a bunch of sort of corner cutting techniques that folks take. You could actually relax the synchronicity of your weight updates. So you can have different workers sort of operate on weights that are slightly out of date. And there's ongoing research in this space to see how to maintain network accuracy while achieving sort of better system utilization by relaxing the synchronization requirements. Okay, so a quick summary of what we've seen. So networks are getting larger and larger. Data sets are getting larger and larger. They take longer to train. They require more resources to train. So scale out is basically the only solution to keep up with those increasing demands. But success at scale out requires optimization and tweaking of many components. You have to have well-optimized hardware as well as software. And software is very important to pay attention to, and that's why we have a portion of the tutorial focusing on software and application experiences today. So hardware-wise, you have to have fast accelerators. You also have to have high bandwidth and low latency networks for communication. Topologies do matter based on which kind of parallelism you use. Some topologies will be more efficient than others. Network switches that can do some math can be helpful by offloading some of the work from the accelerators, so they can sort of concurrently compute and communicate. Software-wise, you need efficient math libraries. So for GPUs, there's cuDNN, cuBLAS, MKL for CPUs. TPUs have libraries as well to effectively use their math engines. You need collective communication libraries. So things like Nickel from NVIDIA or Horovod. These implement collective communications on various topologies in a most efficient way possible. And they keep getting improved. And then you need training frameworks to actually enable various modes of parallel training. So training frameworks, MXNet, PyTorch, TensorFlow, HC32-T1, which is sort of a more specialized framework. And then you need somebody to make proper choices of which parallelism to choose for your particular network. So that can be done manually, and that still happens quite a bit. And then you have packages like Mesh TensorFlow, Gshard, or WSC from Cerebras that we'll hear about later on today that try to automate some of that work for you. And I guess with this, I'll wrap up, and we'll see if we have any questions that I can try and answer.
Thanks very much, Paulius. For those of us attending virtually, it's a little hard to clap, so I will golf clap, and I will recommend that people on the Slack channel, if you're on the Slack channel, please add a comment in thanking Paulius for his talk. We did get a number of questions, and I'll ask them, and as new ones come in, I'll add them as well. So we have about 5 minutes left for the Q&A, which is perfect. Well done on the timing. The first one is from, I'm going to slaughter their name, Iole Mokagata. And they asked, please ask what all-reduce, or explain what all-reduce means, and I might generalize on that, and if you can talk a little bit about the MPI vocabulary for communication patterns, that would be lovely.
Okay. So let me try to back up through slides. I'll talk briefly about all-reduce and maybe some kind of patterns. Yeah, so I really just used a bunch of MPI terminology. So MPI is a message passing library that's been around for a few decades now. It sort of comes from the HPC world, where a lot of the communication patterns have been encountered in scientific computing and so on. All reduce. So actually, I think specifically for all reduce, I guess it's good to look at this diagram, right? So we have an indication of sort of all reduce happening here in our purple section. And by all reduce, what it means is that you collect input portions from everybody, that's the all part, and then you do a reduction, and reduction in this case really means a sum. It's just a terminology in the HPC communication world. So you will see here that each worker carries out the sum. I indicate that with a little circle that has a sum sign in it, but basically it takes all of the data that arrives in it, so sort of submatrices arrive, and it does the sum of them pointwise. So if I get two matrices, matrix from worker 0, matrix from worker 1, I just add them pointwise. So I produce the same size matrix, but now it has, each value is the sum of the two input matrices. And in this case, it's 3. But the more workers you have, the larger sum you have, the more summation you do of various contributions. And the idea after all reduce that now every single worker has all of the sums. So after you've computed the sum, you also have to distribute it to all the workers. So that's, again, sort of the other part of the all. So all means that you take inputs from all workers, and also you give the output to all the workers, and reduction is what you do in between, so you do the sum. Then all gather, which I also, I think, mentioned, that is this pattern here in purple. So all, I guess, again, means that you take input from everybody, so from all workers. But in this case, instead of summing up, you just sort of gather them up. So you take an input from, let's say, worker 0, you take an input from worker 1, and effectively you concatenate them. Right? So rather than adding them, you just sort of put them next to each other. So that's the gather portion. And then, again, you give that output to all the workers. So as soon as you have all, that means everybody's participating on the input side. So everybody, all are doing the input, all get the output, but the operation in between is the gather. And then scatter reduce maybe, or reduce scatter, I'll skip for timing reasons. It's sort of a bit more involved, but again, if you follow these arrows, you'll see what happens in between here.
Great. And there's always time to correspond with people in the Slack channel if there's more detail to talk about. Another question from Manoj Kumar Parmar is about scaling behaviors. I think you showed a U-shaped curve, and that goes to increasing and then flattening and then decreasing returns from adding more workers. Mm-hmm. But I think Manoj was hoping for more understanding about what that means for overall speed up in terms of time to training versus the efficiency. Like, what's the right number of workers to use to be the best at either time to training or how many training runs you could do?
That's a very good question. It's also a very hard question that a lot of people are working to answer today. So, and that's where, as I mentioned, various sort of frameworks came in, like Mesh TensorFlow, G-Shard. They try to make optimal decisions, or some researcher or engineer makes those decisions based on their experience. So, as was pointed out, it is true, as you sort of start scaling out, you'll be doing more and more work if you use data parallel. Or if you use model parallel, you'll be doing more and more compute. Also, as you scale out, you do more expensive synchronizations, so you are adding overhead. So your efficiency, or your scaling out efficiency, will suffer for two reasons. One is application-based, because your convergence may change and you have to train longer to achieve the same accuracy, so you are doing more work. But also your overheads increase as you go to larger scales. So as long as you still keep getting speedups, let's say if I quadrupled my system size and I'm doing slightly more work, I might end up being, let's say, twice as fast as doing work on a smaller system. So it really, I don't think there's a sort of very nice, beautiful, close formula to figure this out a priori. Oftentimes people will try a few things and empirically pick what works best, right? So you don't train the full session, you just sort of examine the performance. And oftentimes, if network is similar to something else that's been used before, more optimal decisions can be made quicker. And I guess I'll repeat myself and say it is an active area of research. There's quite a few people are trying to figure out, okay, how to automate this process to take the burden away from the researchers, from whom we'll hear later on today. So that's also a good question to ask them. How did they make the choices for training scales that they used?
Excellent. We are at time for Paulius's introductory session, and so I will hand off as stand-in session chair and acknowledge Paulius as the actual session chair of the tutorials. So please go ahead with the rest of your tutorial. Thank you very much, Paulius.
Thank you, Cliff. Okay, so I'll introduce the next speaker. So next speaker is Michael Houston from NVIDIA. He's the chief AI system architect at NVIDIA. And throughout his career, he worked on many different things, from chip design to AI system design to deep learning training and language model design and many other things. More recently, he's in charge of designing NVIDIA's AI training servers and server pods, or entire sort of integrated systems. And he holds a PhD in computer science from Stanford University. And with that, I guess take it away, Mike.
Hello, everyone. My name is Mike Houston, Chief Architect for AI Systems at NVIDIA. And today I'm going to talk about how we build DGX SuperPods. So the first thing is understanding data center as an architecture, how we think through speeds and feeds, thermals, deployability, maintainability, operability. So I'm going to talk about our instance of a DGX SuperPod deployment, a machine we call Selene. So Selene is the #1 commercially available MLPerf benchmark machine. It's also the #7 top 500 machine for HPC type benchmark, specifically HPL. It also has a wicked HPCG score. It's #2 on Green 500, and it's the fastest industrial supercomputer in the US. So it's built on a reference architecture that we work with our partners to rapidly be able to deploy systems. It's comprised of DGX A100s, Mellanox, InfiniBand Fabric, and it runs all of the software systems. So things from containers to open source schedulers to enable people to hit the ground running. So in this specific instance, it's actually 2 superpods that are connected. So there's 280 DGX A100 systems, so 2240 tensor core GPUs, and 494 Mellanox switches, and then 7 petabytes raw of all flash storage. So Selene is our 4th generation design that we've deployed internally, and we have many customers that replicate and deploy our designs. So again, architecturally, we think about how to build out the data center and how to deploy these systems. So there's a lot on speed and feed matching, right? How much CPU to GPU to NIC to storage. Thermal and power design, how do you fit into standard data centers without requiring custom build racks? So nothing with ultra high density, allowing us to scale from 7 kilowatt racks all the way up to 50 and even higher kilowatt racks. A lot on interconnect design, which I'll talk more about. And then the bottom 4 are the most important, and these are the big decisions that we made for this design to enable us to be rapidly deployable, easier to operate, more flexible under different scheduling scenarios, hardware failure. And then the big one is expandability. We find that the growth that research teams especially need means that you need a system that can be deployed and expanded and re-expanded without taking downtime and having to reconfigure lots of things in the system. So the first pods that we deployed inside NVIDIA, and we had multiple customers replicate, one example being the Raiden system at Riken, is we had 6 DGX1s deployed. They were connected with InfiniBand, so it was 4 rails of EDR InfiniBand in this generation. And those were cross-connected with blocking factors as we went up in size. So when we initially started, most of our workloads were single node and then began to transition to modest size multi-node, so 4-way, 8-way. And so our initial design was non-blocking to 18 machines. And then we cross-connected those with blocking fabric to end up with larger and larger pods. Okay, so this gave us a lot of flexibility, but in all honesty, it was difficult to cleanly expand because you would hit breakpoints in the director switch designs that we had chosen. We moved to a new layout for higher density designs for some of our customers where we cross-integrated CPU and storage nodes inside our racks, specifically for some of our autonomous vehicle program that needed a lot of flexibility in what they do. So we now handle flexibility a little bit different, where we have GPU and CPU nodes largely done in different racks, which allows us to expand more flexibly in each resource as we need it. Our first design for true high-speed deployment was our DGX2-based SuperPod. So here's a picture of our Circe system. And if you notice way in the back, you'll see the DGX1 design. So this was the first build-out of Circe. We expanded Circe multiple times, and one of the biggest things that we learned was how painful it is to expand machines. So as you hit these switch breakpoints and breakpoints of your scalable units, you ended up having to basically relay everything out and rerun all the network cabling. So this is really painful at some stages to have to basically cut the cables out and redo everything. So at least half the cables had to get cut out during some of our expansions. So we vowed not to do that again because we had customers with the same problem, right? They would deploy 64 DGX2s, and then they'd want to double in size or go from 64 to 96, and it was very difficult to do the expansion. So that's one of the big things that we learned. The other thing that we learned is to better separate our compute, management, and storage planes so we could do different designs and maximize quality of service to enable the highest performance. This was also our first design that was rail optimized, and I'll talk about that a little bit more. So we made a lot of decisions on how we initially deployed our equipment. One of the things that we learned is how you handle thermals in the data center is a pretty big deal. So for those that have been watching CPUs and GPUs now for a few years, there's a lot of clock boosting. And so the more thermal control that you have over your systems, the better all performance you have. And most importantly, for large scale runs, the more consistent your performance is, the less jitter that you have across machines. So we concentrate on cold aisle containment design, but we deploy these in chilled doors. So our last generation DGX SuperPod was a rear chilled door design. We do hot aisle containment, we do no containment. The goal again is how to design everything. But one of the things that we wanted to work through was how to maximize cooling efficiency for the data centers that are being deployed. And again, the goal wasn't to have to custom build like some HPC deployments have to be done. It's designed to be deployed in any data center or colo that you can get space in, or in data center types that people already have. So in this case, we're on a raised floor, and so it was easy for us to do cold IO containment. So obviously we start with a good chip. So an amazing chip in Ampere, and it can do lots of precisions. So we're able to handle many workloads, right? From 64-bit IEEE floating point all the way down to single bit and everything in between. So the SuperPods are built out of DGX A100 systems. There's lots more information online, so I'll be sort of quick through this. So we have a lot of cores to keep all the GPUs busy and deal with all the application threads and some of the IO processing threads that needs to be done. We have a tremendous amount of system memory and interconnect. So the standard shipping config is 1 terabyte machines upgraded to 2 terabyte machines, and it's the 2 terabyte machines that we deploy in Selene. We have 8 NICs that we put on what I call the compute plane. So this is where, as Paulius talked about, this is where all our all reduce, partial reduce, all to all the critical communications that are needed for data parallel, model parallel, and hybrid parallel schemes. And then we have a separate storage plane network that is dual 200 gigabit systems, which allows us to get 50 gigabytes per second into the node off of our storage arrays. And I'll talk a lot more about storage. We have a lot of local NVMe. That's to enable pass-through caching as well as high-speed scratch for things like checkpoints, or people are generating data sets on the fly for training, so for things like reinforcement learning. And then we run standard operating systems. Out of the box, we're currently running Ubuntu. Now, at a high level, it turns out that AI, machine learning, and a lot of HPC codes can be quickly dominated by what your interconnect and storage speeds are. So the whole design of DGX A100 was to match the topology very carefully. So we have dual Rome CPUs. Each of them has 4 chiplets, and we carefully connect our PCIe topology into those chiplets to maximize performance. There's a PCIe switch, and that switch has 2 NICs, 2 GPUs, and 2 NVMEs. So those all happen and can communicate very rapidly together without having to talk through the CPU. So technologies like GPU Direct Storage, GPU Direct RDMA takes a lot of the load off the PCIe connections to the CPU, and things are going in and out of the box very rapidly. And then, of course, we have NV switch connections across our A100s, which allows for very flexible communications. So basically, this is designed to be an IO beast. So here's a picture. This is a snap out of the video that's released that's on YouTube on how we handle cold IO containment. But most simply, we have perf tiles in the floor, and the perforated tiles allow the air to come up. So the machines see cold air first, which reduces a lot of pressure on keeping the whole data center cooled to get maximum performance out of the system. So this is very easily deployable design, and we have multiple people that replicate and deploy this design. So one of the keys to how we design and deploy is modularity. So we have a defined scalable unit. In the case of this generation, it's 20 machines, which matches the radix of the Mellanox switch fabric. It's rail optimized, so there's 8 switches at the leaves that connect these machines together in a scalable unit. That allows us 8 independent rails of sharp connectivity, so we can maximize and have the most flexibility on how our communications are working. So don't take this too literally, because there's different ways to deploy. We shot for 4 machines per rack because this fits in 28 kilowatts, which is the most common high density rack design that we see. We have some customers that need to go in telco racks, and so they will have 1 machine per rack, maybe 2. And then we have some that are very high density customers that may even go up to 8 machines in a single rack. So there's the compute scalable unit, and then we have our compute management fabric. So you can think about this as these are the spine switches, and then you would have another one of these for core switches, depending on how big of a cluster you want to build. Then we have separate out-of-band and in-band management switches. We have various patch panels, common things to be able to route around and keep IPMI and general flexibility up. And then we have a whole bunch of management nodes that do different things. And we have high availability, and so we have replicas of a bunch of these nodes. So the other part of this design is to design for blast radius. So if you lose something, to be able to keep up and running, even if it's in a degraded mode. And then we have storage. So storage is a big one for us, and I'll spend more time talking about our storage hierarchy a little bit later. So you take those modular units, and then you can build them out into pods that are a size of 1,000 GPUs. So For people paying attention, the reason it's 140 GPUs is because our building block is mod 20. So to build a 140 node cluster, you end up with 3 levels of switches: leaf, spine, and core. We design a distributed core, which means that you can now replicate these machines out, and I'll show that to you in a second. So it's a modular fat tree, and so it allows us to build things out. The advantage of a fat tree over something like a torus or a mesh is expandability gets easy. If you deal with a torus and you expand, you end up expanding in one dimension. It's very hard to expand in all the dimensions of your torus. The other thing is, under multi-tenancy, it's very hard to handle proper scheduling placement and deal with some node failures. And then there's also some security implications for some of the workloads that we and our customers need to run, where you don't want data being routed through nodes of a different tenant, especially if it's a competitive tenant. And then this design maximizes Sharp. I believe Paulius talked a little bit about Sharp offload, but allows us to offload a lot of the reduction and communication computation into the switch fabric, which then improves flexibility and performance of this machine. And then you can connect multiple pods together. So you can extend the fat tree fairly directly. Or if you want to scale a lot of these pods together, you can use what's called a Dragonfly Plus. Think about a Dragonfly Plus as a fat tree underneath, and then the top level is a Dragonfly. So again, it allows you to incrementally add these machines as they come online without having to take extensive downtime to build these things out. And that was critical for us having to expand to meet the needs of our researchers, and it's critical the same for how our customers deploy. So it's a little bit of an eye diagram, but I wanted to explain a little bit more on how we lay things out and what I mean by rail optimal. So there's 8 HCAs per DGX A100 on our compute plane. I'm going to focus on the compute plane here. So those HCAs are rail optimized, meaning that they're minimum hop as you're going rail to rail. So most DL applications, including data and model parallel, and most HPC applications, have a tendency to stay rank to rank, meaning rank 0 on one node tends to talk to rank 0 on another node. And if you're crossing ranks within a node, then we use NVLink for those communications anyways. So what's nice about this is we get a lot of redundancy. So if I lose links here, what happens is I lose one of my compute planes, but then others stay up, which means I can continue to run a degraded mode and maintain the compute capacity. So this allows us to keep researchers moving along even under performance degradation without having to take a big swipe through the system if we lose a switch anywhere along the way. We just run in degraded mode. And when you usually checkpoint and restart the application, Nickel will recover and it will find what the topology is and deal with it on the fly. It's also Sharp v2 optimized, as I said before, and so now we can do 8 simultaneous reductions, 1 for each of the compute plane NICs. So here's a literal back of how the machines are wired and how the planes are done separately. So we have compute, out-of-band management, and in-band management that are all separated. And these are all in trays in the machine. So the GPU tray is on top, the CPU and IO tray in the middle, and then all the PSUs at the bottom. So this allows very rapid changes and fixes of anything in case we have a hardware issue in the system. Some initial results on Sharp and why it matters so much for deep learning applications. So the most common reduction sizes that we see are 8 meg reductions for more convolutional neural networks, and then very large reductions, 128, 256 meg reductions for the big things. The sweet spot means is that we turn on Sharp, we get an effective bandwidth amplification of 2x. And so as we get to some of our weak scaling applications, this helps a lot, but it really helps as you get to strong scaling. As your work amount per GPU goes down, you have more and more pressure on your communications fabric. So extracting more and more performance and taking more and more load off the GPU on reductions and putting into the fabric allows us to optimize in different ways and provide the flexibility our users need. The other thing I didn't mention on fat trees is that it's very easy now to map lots of more complicated types of communication primitives that aren't necessarily ring-centric, right? So all reduce, as Paulius mentioned, can work efficiently on a ring, but other communications primitives don't work as well, especially when you have partial all reduces and you're having difficulty placing exactly. A fat tree is no problem to get things across the cluster. So let me talk about storage. So here's a different shot of the pod that you can more easily see the scalable unit build outs, the 5 racks, the 3 and the 2 with the switches in between. So in the deployment of Selene, we use Lustre as our parallel file system. So per SuperPod, we have 10 DDN AI400X units. So there's 20 sitting active in Selene. So per unit, the usable capacity is 2.5 petabyte, the way that we have it set up, and we're just shy of half a terabyte per second per unit. So Selene is 5 petabytes of usable tier storage here for all flash, and just shy of a terabyte per second off a disk. Okay, and the setup is 16.6 kilowatts per one, which is why we have the racks configured and modules that we have to fit the storage, the power requirements to fit the storage in. And then for shared FS, things like home directories, you want an NFS type thing for your Python code to work. So storage hierarchy is a big one, as I mentioned. So you have different levels of caching. So the simplest way to think about it is just like you have data caches on the CPU, you also end up needing data caches in your data center. So there's obviously the memory cache or the file cache, you want to call it that. So aggregate across Selene, we're 112 terabytes per second. Then we have the next level, which is our NVMe cache. We're at 14 terabytes per second on Selene. Then to our Lustre, which is a terabyte per second, and then off to object store. So on-site object store, 100 gigabytes, 200 gigabytes per second is reasonable. And these are things like SwiftStack and Ceph and Dell ECS and things like that. But we can also tier to offsite storage, right? Anything that's S3 compatible. So obviously at AWS, but also Azure and GCP, we can tier to their storage, right, from our cluster. So we view this whole thing and it matches what the hot data set sizes are so that you aren't waiting on data. And some of the problems we deal with are just IO massive, and the amount of data that you need to pull per accelerator in order to run at full speed can be very high. So we were also able to build this during COVID, and there's multiple things we did simultaneously. So we did full bring up of the cluster and build all in one go. We built at scale right off the bat. We were under tight schedules because as COVID hit and we needed to be able to build this, but also to get this up so that we could enable all of our partners, people like Argonne National Labs, to be ready to go when they had their SuperPods coming online. So we did a lot of work on procedures for rapid deployment. Again, scalable unit design helped us a lot, and we have a whole lot of work on DC Ops training material that we supply to our partners to enable them to deploy these machines themselves. So we got a top 10 supercomputer and the fastest available MLPerf system as we're able to build this out. So how fast are we aiming for? So we always want to go faster and make this more simple and more robust to bring online. So we can deploy 140 systems in less than 10 days. The whole thing is designed to be deployable by 2 DC Ops engineers doing 20 systems per shift in a 4-hour shift. So the maximum we were able to deploy was 60 systems in one day across 2 shifts. Obviously, the people get better and faster at doing this. And what limited us this day on the build was actually our loading dock. We couldn't fit more than 60 machines on our loading dock at once. So the general flow is you rack, you do your power up and connectivity check. We have automated provisioning, burn-in, issue identification. Cable wasn't plugged in all the way is fairly common. We do fix, and then we do handoff to users. Our average time from rack to user running is 4 hours in our build. So there's a couple things that we had to do to adapt to go fast. So things you don't even normally think of, like packaging and improving your packaging. So we actually modified how our boxes work to make it easier and more efficient on the DC Ops team to be able to use server lifts with the box and get things up and out and tested very, very rapidly. The shot of the 2 engineers deploying, this happened to be the Friday before lockdown. They were finishing, they're almost halfway, a little bit more than halfway through one of our rows here deploying the machines. So the whole thing was designed, thankfully, to be deployed with 2 at a time. So when COVID hit, we were allowed to, or we were enabled to have 2 people working at a time with PPE and be able to do this with only 2 people in the data center and just continue to build out with all of the admins and provisioning done remotely. We also deployed a robot. So this is a robot from Double Robotics that happens to run at Jetson, but this enables us to move in around the data center so we can check things like link lights, make sure things are okay, especially at 2 a.m. So to go fast, we bundle all our cables off-site. So this allows us to pre-measure, one of the advantages of a scalable unit, and deploy very, very rapidly. So how we do software, so everything we run is done in containers. All of our containers are available on NGC that we run internally, and we support multi-node containers since last September, and this is what we run every day ourselves. Software stack, there's multiple ways to schedule. What's currently running on the cluster is Slurm, plus a lightweight container runtime called enroute, and then a plugin for Slurm to run enroute called Pixis, and then we deploy this with DeepOps. So all this is open source and available, and this is how our customers deploy. We also help customers deploy with Kubernetes-based installations. One of the other interesting things is how some of our workflows work. So from GitLab, people can actually check in code and kick off experiments. So this allows us to build containers on the fly, which means things become easily reproducible. So there's a lot of open source that we contribute to, and this is what we actually use day to day as we run our systems. So there's a bunch of extra links for more information and more depth that are in the back of the slides that you guys can click on and look at. And with that, I'll take questions. Thank you.
Thank you, Michael. Nice talk. We have a few questions from the Slack channel. So we have a question from Mike Evans. He's asking about any approaches to NVMe wear mitigation. And he's also curious about what kind of error correction schemes we employ.
So Paulius, it's very difficult to hear you, but I think the question was about NVMEs. And was it about dealing with write leveling on NVMEs?
Yeah, basically, what is the NVMe wear mitigation? And then what kind of error correction schemes are being used?
Good. So most of our caching is read-only, and when you look at how the caching is done with things like Lustre, GPFS, Weka, there's a few others that cache very well. They have their own various checksumming that they do, so we know the data is correct. And almost all of our caching is read-only. We also have write-only paths for checkpointing. In terms of how we deal with write mitigation, we're striping and carefully monitoring all the NVMEs. The NVMe lifetimes for the workloads that we have are measured in many, many years of write leveling.
Okay, we also have a question on the Sharp slide. The question is, why does the 64M performance look lower than 432 or 128?
Yeah, so this was our early initial work. We continue to tune both nickel and how Sharp works and Sharp integration is done. So this is a speed up slide, which is why 64 looks a little bit less. This could just be a place where nickel was doing a very good job itself on the machine. And there's always a little bit of jitter in scheduling, but the goal is the constant improvements of our libraries to smooth things out like this.
And we'll try one more question. So could you say a little bit more about storage plane and how it can improve efficiency at runtime?
Yeah, so we separate our storage plane out from our compute plane, which allows us to set quality of service most specifically. It also gives us flexibility to run InfiniBand or Ethernet for storage, and customers run both. So you can use things like GPU Direct to get to storage, but one of the reasons that we wanted the NICs on the CPU side is most of the code we see in the wild still has a lot of CPU processing. So we wanted to be able to hit CPU memory and GPUs as efficiently as possible. So caching is a fairly big deal for us. So most of the time you get file caching for free. And so it's a question of how big your hot data set is and how you're sharding, whether or not you need NVMEs. For our data sets at NVIDIA, especially our research problems, the answer is yes, we need to cache to NVMEs to maximize performance. I can probably answer that one a little bit better on Slack. So once I'm done with my talk, I'll get on Slack and start answering as best I can.
Okay, sounds good. I think we're just about out of time, so please join me in thanking Michael. Thanks, Michael.
Thanks, everyone.
And I think we're now ready for the next talk. So we will actually have two speakers. We'll have Samir Kumar, who's currently at Google Research, exploring scaling machine learning systems and training on Google TPU accelerator systems. And prior to that, Samir worked at IBM T.J. Watson Research Center, also studying message passing libraries and massively scaling to supercomputing scales. And Samir holds a PhD from University of Illinois. The second speaker is Dehao Chen, who currently works in Google Research, focusing on scalability and performance optimization for TPU systems. He holds a PhD from Tsinghua University, and ever since graduation, he's been at Google working on compiler optimizations for various systems. So with that, Samir, please take it away.
Good morning and welcome to the Hot Chips tutorial on machine learning scale-out. My name is Samir and I will be co-presenting this tutorial with my colleague Dehao. First, a brief overview. This talk is in two parts. First, I will present the scalable architecture of TPU multipods and the fast scalable collective implementation. Next, my colleague Dehao will present scalability techniques like weight update sharding and model parallelism, followed by performance results and a brief conclusion. So the space race for the biggest ML training machine is on. This began with Microsoft Azure acquiring 10,000 GPUs for OpenAI to train very large language models. OpenAI trained the generative pre-trained model, GPT-3, and we all know how successful that has been. I'm sure by now my colleagues in NVIDIA in the first two presentations would have given us a background on DGX superpods with 2,000 GPUs. This is a very powerful machine which is very tightly interconnected. At Google, recently we designed TPU multipods with 4,000 chips, and in this talk we'll provide more details on the multipods. But first, we'll begin with an overview of the Google Tensor Processing Unit that has been around for over a year now. On the left, you will see a picture that shows a card with 4 chips. Note the copper pipes, those are actually for water cooling. And this card can achieve a peak mixed precision floating point throughput of 420 teraflops with 128 gigabytes of high bandwidth memory. These cards can be scaled out and connected in a pod configuration that is shown in the right picture. A TPU pod has over 100 petaflops of mixed precision compute, 32 terabytes of HBM, and it's interconnected in a 2D torus. The cables you can see are the TPU torus cables. We extended the 1,000 chip TPU pod configuration to a 4,000 chip TPU multipod configuration. In a TPU multipod, we interconnected as a mesh along the x dimension of size 128, and the y dimension is a torus, and it remains the same size as a TPU pod, namely 32. And in this configuration, we enable more than 400 petaflops of mixed precision compute. This machine was used for Google's submission to MLPerf training v0.7. A brief overview of TPU system architecture. TPUs heavily rely on 128 by 128 systolic arrays that provide bulk of the compute for matrix to matrix multiplication operations. While the vector operations execute on the MXU, there are also scalar operations executing on scalar units. And typically these perform data formatting or reductions that can be executed concurrently while the matrix unit executes vector operations. There is on-device 16 gigabytes HBM storage. There's 2 stacks of it, and it's connected to the MXU via a on-chip interconnect. a brief overview of the TPU v3 software stack. When the neural network model is developed in TensorFlow, it would be compiled to a TensorFlow graph, and then the TensorFlow graph is then converted to an XLA higher level operation graph, and then the higher level operation graph is then converted to TPU machine instructions. This is executed just in time and compiled individually for each slice at the time of the job launch. This allows us to optimize the instructions for a given job. We enable several communication primitives such as all reduce, all to all gather, and send receive to enable hosts and accelerators to communicate with other accelerators on the 2D torus network. We enable multiple programming paradigms. Both flavors TF1.x and TF2.x are enabled on TPUs. We also more recently developed the JAX programming model, and this is a NumPy field programming model. It has a NumPy field to it. It essentially enables composable transformations of Python. JAX is a multi-client programming model similar to other HPC programming models in the sense that each worker can compute its own operational graph, and workers typically synchronize with other workers through global communication operations, for example, all reduce. We also support flavors of PyTorch on TPUs. So what are the challenges of large-scale training? The biggest challenge, of course, is to execute linear algebra at extremely high throughput, and this is enabled in the XLA compiler. In addition, we need fast communication primitives, for example, gradient summation. And in addition, especially when model parallelism is enabled, we would need fast send receive, all-to-all, and other communication primitives. In addition to high linear algebra throughput and communication optimization, one of the challenges we had to face was to increase the availability of a large machine. For example, if a ML scientist wants to train on 4,000 chips, then the 4,000 chips need to be made available so that the model can keep training. One of the approaches we found useful was a firefighter approach, where we have a crack team of firefighters in data centers that can go and replace cards when they break in a fairly short turnaround time, and then the model can start training again. Other approaches we have explored include high availability, all reduce algorithms where we execute the all reduce on a mesh even with failed hosts. In addition to increasing the availability of the machine, another challenge is scalable launch of ML ops. And typically in a model like TensorFlow, which provides a unified view of the accelerator, where the Python executes ops on the accelerator as a single device, these ops need to be pushed to the accelerator on all the nodes as quickly as possible, executed, and then the graphs need to be brought back for checkpointing or any other user level Python tweaks that may be applied by the user. This also requires us to initialize weights on TPUs very, very fast. Another challenge we faced was in optimizing host input pipelines. And typically when all the machines concurrently hit the file system may process them in an order where some requests happen a little bit later than the others, and this could trigger jitter. And this would force a TPU accelerator to arrive, for example, at the next all reduce later and potentially block the entire machine. We found a nice technique of prefetching to minimize the impact of jitter. In prefetching, the input pipeline would move ahead of the device pipeline and buffer examples. So the next time when there is jitter, the input pipeline would just go into the buffer, and if the input pipeline throughput is higher than the device throughput, typically when everything is functioning well in the file system, the input pipeline can start making more examples. Quick overview of ND meshes and tori. Each node is connected to two neighbors, while bidirectional links, in the case of a mesh, edges and corners are not connected to the wrap links. In the case of the torus, they are connected to the wrap links. It's optimized for near neighbor communication, and all-to-all traffic can be bisection limited. A great example of near neighbor communication is all reduce on a 2D torus. And to execute all reduce on a 2D torus, we would split it into several ops. So the first op would do a reduce scatter along, let's say, the columns. And that would be phase 0. And then in phase 1, the reduced shard from the reduced scatter would be further summed along the x dimension. In this case, we call it phase 1. And that'll reduce an even smaller shard of size 1 by n, where n is the total number of accelerators in the mesh or torus. And then this is followed by 2 phases of gather, where the summed shards are first gathered along the x dimension and then the y dimension. When it is executed in this way, we could make it concurrent, where rows and columns could do the first phase concurrently on 2 different subsets of data. We call this a multicolor algorithm. And then the same could be repeated along the x dimension for phase 1. And this would potentially give 2x higher throughput. The reduce scatter all gather approach in general is also known as the ring algorithm on meshes and tori. So how do we do this on a multipod? Note, a multipod has a significantly longer x dimension. So what we would like to do is to maximize communication volume along y dimension, which is 32 chips, and it also has the wrap links. So we can make the rings bidirectional. So we do the first phase on the y dimension, and the little shard that comes out of the first phase is then summed along the x dimension, which is predominantly latency bound. And when it is executed this way, we have noticed very high communication bandwidth. It was sufficient to get the MLPerf results we get. In the next part of the talk, my colleague Dehao is going to discuss scalability techniques. Thank you very much.
After we build such a large system, the next step is to scale our workload to train efficiently on it. We all know that it's very difficult to program for a very large system, and we don't want to pass these difficulties to the user of the system. So when we initially design a software stack for the system, we want our compiler to automatically optimize for both performance and scalability. And we also want to design very simple API that can combine with the compiler optimizations to partition the model and enable model parallelism. Both of these topics would require 1 day of tutorials to cover most of the interesting topics, but today I will focus on one example from compiler optimizations and one from model parallelism to demonstrate how we scale our model training to such a large-scale system. So first, let's take a look what's happening inside a typical training step. So in synchronous training, the way how it works is that the input feeds into the forward pass, goes through the backward pass to get the local gradients, which is accumulated across different replicas and feed into the optimizer to update the weights. So the portion of the all reduce and weight updates differs from different type of models. For typical image models, they usually have small weights and large inputs, thus the all reduce and the weight update portion is relatively smaller. But for the sequence models, they usually have relatively large weights and small inputs and activations. So the portion of all reduce and weight update are relatively larger. So one typical way that people use to scale the model to more computation resources is that they keep the global batch the same, but increase the number of replicas. So this way, the per replica batch size becomes smaller. So the total compute needed to finish the forward and backward pass also scales linearly. However, if you look at the all reduce and the weight updates, because they are operating on the weights instead of activations, so batch size does not come into play. So this is the constant part of the training step, and based on the Amdahl's law, it will quickly become the scalability bottleneck, especially when the per replica batch size is small. So let's look further into what's happening inside the weight update part. So a lot of those optimizers use element-wise operations, which are memory bound. And because of this, they are also very sensitive to the number of optimizer slot variables. For example, for add-on optimizers, they are usually 2 to 3 times slower than SGD because they have two more slotting variables. So we noticed that in this training setup, all the weights are replicated across all the replicas. And so is the corresponding weight update operations. So an intuitive way to speed this up is to shut the weight update operations. So the way we do this is that we first split the all reduce operation into two operations. The first is a reduce scatter operation, which is basically the same as all reduce, except the output only has one shard of correct accumulated inputs. The second operation is called all gather. So for each replica, it sends its own valid shards of data to all other replicas. And during the meantime, it also receives the valid shards from other replicas and concat them together locally to produce the full shape of inputs. So in this way, these two ops combine together to perform the original all reduce operation. But because it's split, we are able to have the compiler perform some code motion to move the gather operations across the weight update operation to where it's actually being used. So this way, the weight update operation does not need to operate on the full shape, but can just operate on the sharded part. So this is the high-level idea of the optimization. So the way we implement this in our compiler is that outside the training loop, we first shard both weights and the slotting variables. And inside the training loop, whenever the weight is used, we insert an all gather before the use. And also we insert a reduce scatter after the local gradient is computed. And then we change the weight update op to only operate on the sharded weights and gradients. So this is all automatically done by the compiler. So it's transparent to the user. So there's no model change needed to enable this optimization. So if we look at the performance, so weight update part of the training step is basically scaled down linearly by the number of shards. So it becomes much faster than before. And if we keep the data type of the reduce scatter and the all gather the same as the original all reduce op, then the two op adds together will be the same time compared with the original all reduce operation. But one thing to note is that we have added another optimization in XOA, which will take a look at all the uses of the weights. So if all of them are in reduced precision, which means bflow 16 for TPU, then the compiler will automatically convert or gather operation to the bflow system as well. So unlike the traditional flow 32 or gather, this will speed it up by 2x. And it will further speed up the convolution performance that uses these weights, especially for those convolutions that is bounded by the loading of weights. So besides performance, this optimization also saves memory. This is because there is no full shape reference of the slotting variables inside the training loop. So compiler can automatically split the life range of the buffer that's used for the full shape of the slotting variable and reuse that for other activations inside the training loop. So this memory saving is extremely important when you want to scale a model to very large size. So weight update sharding turns out to be very effective for data parallelism, especially for cases where the per replica batch size is small. But if you already have relatively small per replica batch size and want to further scale your model to more computational resources, model parallelism can help here. So there are a lot of different types of model parallelisms that's supported on TPU. So we have graph partitioning, where user just annotate on the model about which part you want to run on which device. And the compiler will insert the necessary communication and optimize that to overlap with computation to make it as efficient as possible. We'll have spatial partition, especially for image models, and I will talk about in the next few slides. And we also have pipeline parallelism called gpipe, which is very effective for models that are very deep. And finally, we have gshard, which is a general way to partition both weights and activations for a model for scalability. So my colleague Zhifeng will talk into more details about gshard in the next session. So let's take a look into what is spatial partition. So we know that for image models, most input and activations will have two spatial dimensions, width and height. So if you have a model that takes very, very large inputs, for example, those super resolution models, or for medical images, which are usually very large, so sometimes the input itself will be too large to basically fit into the whole device memory. And also, even it fits, because of the batch size is relatively small and less efficient, you may want to basically just partition the spatial dimension instead of batch dimension to make it more efficient. So the way you do that for TPU is that you just need these two lines of annotation in your TPU config, and the compiler will take care of the rest. So it will automatically split the infeed and the set to different devices. It will automatically generate a convolution code that handles both within the shard and the cross-shard computation and the communications correctly. Because when you are actually performing the convolution at the boundaries, sometimes you do need to get data from other shards. So, and additionally, it also takes care of automatically switching between the sharding and the replication. This is because at the end of the convolution model pipeline, usually spatial dimension becomes too small, so partition it becomes less efficient. So we have a good performance model to indicate when should we switch from the partition to the replication. So all these are handled automatically by the compiler with only two lines of annotation by user. So we applied this spatial partition on one large RetinaNet model with large inputs for training, and also a small ResNet, small input and inference model. We can see that the scalability for the large RetinaNet model is really good all the way to 8 devices. But for the ResNet, the scalability is not that good because a lot of constant factor come into play. But we still get positive speed up, which could be still a good use case for the strong scaling. So finally, we have applied all these scaling techniques to a lot of models in Google. So including all these performance compiler optimizations and also model parallelism. And we also apply this to our latest MLPerf 0.7 submissions. So with the help of these techniques, we managed to scale a lot of models to the 4000 chip TPU V3 chip system that Samir just mentioned, and get really good performance. To summarize, scaling workload to large systems is very difficult. So you need to have very fast and flexible interconnect, and you also need a lot of software innovations to remove bottlenecks in scaling, and also to enable users to automatically benefit from all this efficiency from large-scale systems. So if you do have such very large systems, which you should have because you can always run it from Google Cloud, and if you want to scale your model up into these large systems, model parallelism could be very helpful here. That's all for my talk. Thank you.
We have a question from Dan Wilkinson. He's wondering about how the 2D torus topology interacts with high availability for the system. For example, what happens if a link or cable is broken or not plugged in correctly? Dehauer and Samir, did you guys get a chance to hear the question? Am I live? Okay.
Paulius, can you speak up? I cannot hear you.
Yeah. Okay. I think, all right, so we have time for a question. So one question is from Dan Wilkinson. He's wondering about 2D torus topology and how it relates to high availability of the system. For example, what happens if a link is broken or cable is not plugged in properly? How does the system deal with that?
Sure, I can answer that. There are a couple of things we do, as mentioned in the talk. First is the firefighter approach, where we go and fix it. And alternatively, we have also explored high availability techniques where we can route around failed links or failed chips. Okay. So both approaches should work well.
Okay, thanks. I'll squeeze in one more question. It's from Adrian Lotianu. I hope I'm pronouncing the last name correctly. He's wondering how the 128 by 128 systolic array dimensions were chosen. Why not something smaller to work with smaller matrices?
This was mostly based on internal experiments, on internal workloads, to identify what's the best that works for our internal workloads, and 128 seem to have given the best throughput for our internal workloads overall.
Thank you. Since we have a minute remaining, I'll ask yet another question. So Kevin Hunter was wondering whether there are any acceleration features for sparse weight matrices.
Embeddings are important in training, and we do support embeddings, yes.
Okay, I think we're out of time, so please join me in thanking Samir and Dehauer. And with that, we'll start transitioning to our next talk. So our next speaker is Natalia Vasilyeva from Cerebras. where she's a senior technical product manager. She's focusing on machine learning and artificial intelligence, analytics, and application-driven software hardware co-design and optimization. She holds a PhD in computer science from St. Petersburg State University. And with that, Natalia, please take it away.
Thank you, Paulius. And good morning, everyone. Hope you can hear and see me. So far, Paulius did a great job telling you what it actually means to scale out deep learning training and how you can use multiple devices to run a single job, how you can do that across multiple GPUs or across multiple TPUs. And essentially, the truth is that with today's state-of-the-art models, it will take too long to train a model on a single device. So scaling out has been the only way to cope with these extreme computational demands of training so far. But we also know that when you start distributed work, essentially all your mental cycles target the task how to reduce communication bottleneck. So the success of distributed training, the successful scaling, depends on if you are capable to hide communications behind the computation, if you can come up with a very efficient communication in the hardware, if you can come up with a very efficient algorithms which can enable those multiple workers to talk really, really fast. At Cerebras, instead of kind of scaling out across multiple devices, we just design very large chips, very large processors. And then the task for us is how we can distribute a training job across all of the cores, all of the processing elements within the chip. And in this talk, I will talk how we do that. So for the audience of this conference, probably this picture is obvious to recognize or to understand what's that. It's a wafer divided into dice. So every single processor starts its journey being kind of packaged on a wafer. So you have multiple copies of the integrated circuits on the same piece of silicon. But then they are taken apart, so the wafer is broken. We package them independently. Every single one of them becomes an independent processor chip. And then we spend kind of enormous efforts coming up with sophisticated communications protocols, interfaces. So we use PCIe, NVLink, InfiniBand, a lot of wires to connect those chips back together. And when you have a workload which requires computation across multiple chips, you need to cope with this communication. So it's essentially like breaking down Humpty Dumpty and then trying to put it back together. At Cerebras, we decided to do not break Humpty Dumpty and just keep the wafer whole. So instead of breaking down the wafer, we integrate connections between different dice, and we cut the largest square out of a single piece of silicon, out of a wafer, which we can, and essentially that's our chip. So this is Cerebras wafer scale engine. It is the largest processor chip fabricated on a single piece of silicon. It's more than 46,000 square millimeters. It has 1.2 trillion transistors, and it powers 400,000 cores optimized for deep learning. All of those cores are fed by 18 gigabytes of on-chip memory distributed across all of those cores. That memory is really fast, which has some advantages for low batch training. And what's important for kind of distribution, all of those cores are very tightly connected to each other. So we have 100 petabits of bandwidth, fabric bandwidth between the cores on the chip. And that's due to the fact that all interconnects are in silicon. So we don't need to overcome long distance communication. We don't need to overcome other complexities. This large chip is hosted in a Cerebras system called CS1, which delivers power, cools down, and delivers data to the chip. But today I will be mostly talking about how we distribute work across those 400,000 chips. So 400,000 cores, sorry. So our processor is essentially 2D mesh of 400,000 fully programmable processing element. So every single one of them has its own functional control units. It has local memory, and it is kind of optimized for linear operations on sparse tensors. And all of those processing elements are tightly connected with on-chip fabric, with on-chip communications. So that enables us to use a diversity of distribution strategies to kind of parallelize the work across all of those 400,000 cores. So how do we leverage all of those cores? And again, the secret here that all of these are tightly connected to each other. So we can essentially use exactly the same approaches, as Paulius reviews with you. So use model parallel, different types of model parallel, and use data parallel. And we are not bottlenecked by communication. So as a result, we kind of use a blend of those strategies. And that blend is very, very flexible. So for every specific model, we can choose, depending on the computational demand of the model, how much we want to use model parallel within the layer or intra-layer, like Paulius called it, or how much we want to pipeline, how much we want to rely on data parallel. It also depends on a particular model, and the exact strategy, exact distribution strategy, is chosen automatically by compiler, which essentially during the compilation solves an optimization problem and trying to see which combination of all of those modes of parallelism is the best for this specific model. So you can use all of those parallelization strategies with the traditional devices as well. And I like to think that when you start training on standard devices, GPUs or TPUs, typically you have some amount of parallelism within a single device. So if you have kind of one worker running on a single device, you still do parallel computation. And typically it is a model parallel within a layer. So you do computations on a bunch of parameters within the layer. That happens in parallel because all of those chips are also quite sophisticated. They also have large number of cores, not for 100,000 cores, but also thousands of cores. So they also can rely on that parallelism. But then you start kind of add workers, you start add devices, and you do that in bulk. So you add one more device, and typically you need to decide, when I add one more device, which parallelization strategy I would like to choose. And as Manny mentioned before, the easiest one to use, at least as long as you fit your model within the single device, and as long as you don't suffer from kind of lack of convergence for extreme batch sizes, which is caused by desire to use a weak scaling and still keep the utilization of the hardware high. So you will use data parallel. So you will add a number of cores which belong to an additional device, and you will do model parallel training. Sorry, data parallel. You will add an additional device, and you'll, again, like increase the degree of data parallelism in your training process. At some point, again, your model doesn't fit into the single device, or you want to rely on model parallel for some other reasons, you can choose to add model parallel. But again, it happens in bulk. So you add a new set of cores which belong to a new processor which you add into the problem. At Cerebras, instead, we kind of have this continuous space of all possible distribution strategies. And depending on the model, we can choose any point in this space, and we can decide what's the most optimal amount of layer parallelism, what's the most optimal amount of pipelining, what's the most optimal amount of data parallelism for this specific model. And it's very flexible. So let me talk about kind of each of those in details a little bit. So we'll start with the model parallel within a layer. So we distribute execution of the single layer across multiple processing elements, PEs, and compiler does a job for you to choose the optimal number of those PEs and the optimal shape for every layer. So typically compute-heavy layers, like this orange one, gets larger PE allocations, so they get a larger fraction of the fabric of the chip. And then less compute-intensive layers, like a yellow one, get allocated less number of cores. And we run kind of in parallel execution of single layer across multiple processing elements. So let me walk through an example of one simple layer, which is fully connected layer, which is essentially matrix vector multiplication. So we always keep the weight of the model stationary to the chip. We distribute that across multiple processing elements. So each PE gets a tile of weight matrix. On this picture, every green, let me see if I have a mouse here. Every green rectangular represents one processing element. So each of them holds a portion of the weight matrix. And then we start streaming input, activations from the previous layer, or just input data, either from vertical direction, or it could be also kind of transposed and streamed from the horizontal dimension. And output comes on another side. So for example, let's say we have an input of length 8. Our output here will be also length 8. What happens here, each PE will work on a subset of elements of my input vector. And like those elements will be broadcasted to all the rows of processing elements. So this blue guy will broadcast it to this processing element and to this processing element. This orange will be broadcasted to this guy, and so on. So at every, we will start with kind of just multiplying all the weights which we have local to this PE to the input. And then we will proceed with our add accumulates. So at the end, kind of every tile will contain partial sum of the result of kind of part of the output. And then we accumulate all of those partial sums and then produce the output. And again, kind of every, we will have part of the outputs produced by different tiles. We can hide the latency of partial sum accumulation with input activation streaming. So essentially, we'll start streaming inputs and kind of go from matrix vector multiplication to matrix multiplication and completely hide that accumulation. So that allows us to kind of distribute computation across multiple Ps for a single layer. But we also heavily rely on model parallel layer pipeline training. So essentially, we always try to fit the whole model into the chip. And it like helps us to avoid moving weights back and forth between off-chip and on-chip memory. It's always on-chip. It's a very beneficial strategy. And what happens, portions of the fabric get allocated to specific layers or block of computations in neural network. So in this cartoonish example, again, I have my simple neural network with several neurons per layer. Amount of processing elements allocated per layer will be proportional to the compute intensity of a particular layer. And then we will place kind of adjacent layers next to each other, and the data will just flow through. So we'll start streaming the input, let's say, from this vertical direction into this orange block. It will do vector matrix multiplication, stream the output to this blue portion. This will do its own job, stream output to green, and so on. And during the backward pass, we will just repeat in a backward order. And this layer pipeline execution is really good, again, because you keep all the model on chip. All the downsides for layer pipeline execution mentioned by Paulius before are mostly because of their extreme communication demands. But because that doesn't matter for us, we have enough communication bandwidth on the chip, we can sufficiently leverage that method of parallelism. But for some models which are, and yes, layer pipeline execution can be used in the standard clusters as well, but it is challenging because you have limited communication between devices, and essentially you have to shoehorn your layers into fixed amount of compute. So let's say I have a 4-layer network and I have 4 devices available to me, either in the system or in the cluster, and then I need to choose like how to divide my neural network between those devices. And this comes at expense of this load balancing, which was also mentioned before. And also, typically, this choice is done by ML researchers. So he needs to think, what should I prefer? Either underutilize, like on this picture, devices 4 and 3, or should I pack together my yellow and green layer, and I will just not use one of the devices at all. On CS1, this layer pipeline execution is very easy and efficient, and that's because our kind of pool of compute is very flexible, it's very fudgeable. So instead of having like fixed units of compute, we can allocate, you can think about them as virtual devices, and each virtual device will have just right amount of cores for this specific layer. So you can optimize the whole placement of the workload on the chip towards the specific model which you're trying to train. So model parallelism is our kind of primarily way to distribute computation across the cores. But for some models which are small, we still also add data parallelism into the mix. But we do that also slightly different compared to traditional clusters. So instead of replicating kind of the whole model and placing like one model on one device or one portion of the fabric and another replica on another portion, we replicate layer by layer. So we'll have several replications, like on this picture of the first layer, like 2 replicas of the second, and so on and so forth. It helps us to kind of keep communications local, so only parts of the kind of orange tiles will have to talk to each other. They will also have to exchange the weights only of that single layer. So you don't need to communicate kind of the whole model between all of the replicas. And that helps to speed up everything. So in the summary, wafer scale engine uses a blend of parallel execution modes, and this kind of a fudgeable blend. So we have single algorithm which will use both types of model parallelism and data parallelism in optimization. So given a model, it will choose the optimal placement strategy for that model on the chip. So if we have a model which has few very large layers, we will mostly rely on model parallel within the layer, so intra-layer model parallelism. So every layer will get allocated a significant portion of the fabric, and we will distribute that across that fraction of the fabric. When we have deeper models, which have more layers, then we will more heavily rely on layer pipelining. So we'll still keep all the model on the chip, and probably there will be less degree, smaller degree of intra-layer parallelism, because every single layer will get less cores, less processing elements allocated to that, but it will be more of a layer pipeline execution. And for small models where we can't leverage the whole chip with model parallel execution only, we add data parallel and we start to replicate some of the layers. So this all gives us a very good way to distribute workloads across the chip. But we believe that scaling in deep learning is not only about efficient distribution. It's also about flexibility of the compute, and it's about ability to kind of support different types of computation. And let me explain what I mean by that. So I believe personally that future path for better models, it's not only on kind of large dimension, but it's also when your models become smarter, when you innovate in algorithms. So brute force scaling, when you just increase the number of parameters and replicate the layers, has been historical path, especially in natural language processing. Maybe less so in computer vision, because computer vision is more mature. So if you look at, I don't know, from BERT, from GPT to Megatron to Microsoft model, then to GPT-3 by OpenAI, which is not on this slide because otherwise all my points will be scrambled into one corner. They're all about essentially replicating the same structure of the layers. You make your model deeper, you make your model wider, but you still use every single data point for updates of the model. And it's very challenging. So your memory needs to grow on the computation side, your compute needs to grow. And when we're talking about desire to train a 1 trillion parameter model, it's not clear how to do that. So yeah, we can rely on data extreme scale out, but it's also very hard. So I think that we also need to look into algorithmic innovations and into some techniques which enable us to reduce computational algorithmic complexity of the models. Ideas around reusing some of the weights, which will allow you to reduce memory demands. Ideas around using sparsity. Ideas around using computational, conditional computations. Like Google recently trained 600 billion parameter language model. But they were capable to do so only because they use conditional computation. So essentially, they don't use every single data point, every single token to update all the models in the parameter, all the parameters in the model. And that's essential for the hardware to be able to support that flexibility. So to be able to choose that I would like to do operation, specific operation only on one specific data point. So I don't do my computations in bulk. And that's what CS1 is kind of designed to do so. There are two key properties of our architecture which position us, I believe, uniquely to support those models. First is wafer scale engine. CS1 is essentially data flow architecture. So we have a flexibility to stream data at a very fine granularity. We can stream data token by token. We can stream data pixel by pixel for images. And it makes it very easy to harvest sparsity. It makes it very easy also to kind of adjust for irregular shapes of tensors where we do different operations. And also, the second very important property is that CS1 is essentially MIMD architecture, so multiple instruction, multiple data. That means that we can program each core independently. Every single processing element can do completely independent work on completely independent data from all of its neighbors. So its extreme flexibility enables us to kind of leverage those conditional computations and to leverage those ideas how to reduce model complexity, algorithmic complexity of the models. So let's look at some of those techniques which have been proposed in the past. So we'll go first through kind of first column, describe the techniques, and then comment on them. So some of those ideas to share weights between different layers, like in Albert, allows us to reduce memory requirements for the computation. So essentially, the number of parameters in your model becomes less, although you still kind of have a very deep model because you reuse the weights in different layers. It typically tends to increase in the compute because you still want to have some capacity in your model. I probably don't want to build a 24 layers of encoders model and reuse weights all the time. I might need to make my model a little bit wider, which will translate in more computation. But still, like, you can get to the same accuracy in significantly reduced model size. And this technique is very well suited for both SIMD engines like GPUs and TPUs and to CS1 as well. All of us can use that reduction in memory footprint. The rest of the techniques are mostly targeting kind of reduction of algorithmic complexity of the model. So they're trying to reduce the number of flops which you need to make in order to train the model. So some ideas around dynamic depths and use this conditional computation when essentially represented in universal transformer, when essentially on, like, even per token, you can decide how many transformation I would like to make on that token, like how many layers deep I need to process to get a good representation for this specific token. And when we come to granularity of this per token granularity, it becomes extremely difficult for SIMD engines to support because they leverage this, they are single instruction, multiple data. So they want to do the same instructions on many data points. And when I would like to do, I don't know, 5 layers for token number 1, 10 layers for token number 2, it becomes very kind of inefficient on SIMD engines. On CS1, because we are an MIMD architecture, we can do that. And we actually significantly reduce flops and speed up training, leveraging those conditional computational ideas. There are a lot of ideas on sparsity, either inducing sparsity in activations, having some natural sparsity using ReLUs, or just inducing sparsity artificially, which can also translate naturally into speed up on CS1, and which is much harder to leverage on SIMD engines. Some ideas around attention sparsity. Essentially, whenever you do operations on sparse tensors, it's very easy to leverage and to translate it directly to speed up on CS1. Also, there are some ideas around like using neural architecture search, like models like a wall transformer, where you essentially explore the shapes of the layers. And as a result, typically those layers becomes very, very irregular. So it's not nice duplication or replication of the same shape like in BERT-GPT-2, but you have all the layers of different shapes. And if you want to use something like layer pipeline parallelism or some other forms of parallelism, dealing with these matrices of different shapes is challenging on SIMD. But again, on CS1, we can handle that perfectly well. So kind of concluding, Cerebrus wafer scale engine is a 2D mesh of 400,000 programmable processing elements. All of them can be individually programmed, so it's a MIMD architecture. We leverage a wide blend of parallel execution strategies, so we rely on model parallel, all types of model parallel, and for smaller models, we add data parallel into the mix. And our graph compiler automatically chooses the optimal blend of those execution strategies. And as a matter of fact, in another talk on Tuesday, one of our co-founders, Sean Lee, will show some of their results of scaling with the different parallel approaches and how that results kind of in speed on wafer scale engine. That freedom which we have in choice of different distribution strategy is thanks to the fact that we not limited in memory bandwidth, and we are not limited in communication between different cores. So we have extreme memory bandwidth, and we have very high connectivity between all of the cores. So we can afford to choose this fudgeable blend of distribution strategy and choose whatever is best for a specific model. And the last, the fact that our hardware is actually multi-instruction, multiple data, and it is a data flow architecture, enables us to support this next generation of models. And I personally am a huge believer in those conditional computations and sparsity induction in any way that can reduce just sheer algorithmic complexity of the model and get to the same quality, but with less flops. And we make sure that we compute only those flops which are required. So that's a way to better models and to more accurate models in the future. So essentially we have, on the single device, we have performance of the cluster, because we have like all of those dice kept together and number of cores equivalent to number of cores which you will get across multiple devices in a cluster. But it is ease of use of single device. You don't need to think how you distribute that. Compiler does that for you. You program it as a single device, and it's a very easy, it's a very good experience for a machine learning researcher. And we also have unique flexibility to support these new types of models which are coming out. Thank you.
Thank you, Natalia. We have actually a very large number of questions in the Slack channel, so I will try to sample some of the more popular ones. And sort of as a note to everybody who's asking questions, if you sort of vote for popularity of the questions, they help us sort of prune them out and ask the speakers.
And I promise to get back to the Slack channel and answer some of those.
Great. Okay, so we have actually two people asking a very similar question, so I'll combine them. So it's Vishwas Vedantam and Tom Gooding. They were wondering what happens with either link or node failures. Does that imply that the entire wafer fails, or is there some kind of routing mechanism to deal with a 2D mesh cut through and so forth?
Yes, so we have redundancy mechanisms built into the chip. So essentially, because we have very homogeneous design, so all our processing elements are exactly the same, and we have a very large number of those. So we can afford to have failures in some parts of the wafer, and then we will just mask that portion of the wafer, and we will route around. So we have redundant cores, we have redundant communication routes around those cores, and even if some parts of the wafer are not of high quality, essentially to the programmer, we still produce a homogeneous 2D mesh of those cores. And so far, we've yielded every wafer that has been produced. So unless TSMC is screwed up and have all the failures in one corner of the chip, and then we will just don't take that chip, we are good.
Sounds good. We have a question from Cliff Young. So his comment is that it seems that the model parallel layer pipeline approach could lead to very deep pipelines or very large pipeline depths. For example, looking at a network like ResNet 101, you probably would have over 300 deep pipeline for both forward and the backward pass. So what has been your experience with these very deep pipelines, given that a lot of other pipeline parallelism work has been focusing on very shallow pipelines to reduce communication? So what's been your experience with very deep pipelines when it comes to convergence and time to train?
Yes, so I think for convergence, there are two modes of training on our device. One of them, we support kind of vanilla stochastic gradient descent, and supporting deeper pipelines results in a larger batches, and batch will be proportional to the depth of the pipeline. But still, those batches are not extreme. So if we're talking about, I don't know, pipeline of 100 layers, your batch size will be around 1K, and that will be enough to kind of hide the overheads, what we call fill and drain of the pipeline. So we can support deep pipelines. If you want an exact stochastic gradient descent, you will have to increase slightly the batch size. But again, it's far from very extreme batch sizes, which are used in data parallel scale-out training. And another mode, we also work on a kind of continuous backpropagation. We have a paper published at ICLR, I believe, on continuous backpropagation, and that allows us to essentially make updates, to do asynchronous updates to the model. And in this case, we don't need to kind of fill and drain the pipeline, and we can continually stream the data.
Okay, thank you. We have a question from Ridika Borkar. What precisions are supported by FMAC units?
Yeah, so we support IEEE FP16, IEEE single precision to 32 bits. We have also in hardware support for our own version of FP16 format, which has kind of more bits for exponent and less for matrices, so you get the higher range but lower precision. Most of our neural networks internally today trained with mixed precision similar to NVIDIA approaches, so we do all multiplies in FP16 and accumulates in FP32.
Okay, thank you. I think we have some time for a couple more questions. We have a question from George. What is your solution whenever the problem requires more than 18 gigabytes of memory?
Like everybody else, to scale out.
Okay.
It's just we start to scale out at a different scale.
Okay. And maybe one last question. What kind of latencies are seen in reconfiguring the machine to suit a different model, a different distribution of the model?
Yeah, so that's a good question. So typically we configure the communication patterns for a specific model, and we understand how to place the layers during the compilation. So the compilation of small models takes maybe a minute. Compilation of larger models can take a few minutes, but that time it's still kind of significantly smaller that you would spend on the training.
Thank you. I think we're out of time for this session, so please join me in thanking Natalia.
Thank you, everyone.
Research group, where he manages the NLP team. His team focuses on language modeling applications such as question answering, dialogue systems, and as part of their daily life, they face a lot of large-scale training sessions. He holds a PhD from Stanford University. With that, Mohammed, please take it away.
Thank you, Paulius, for the introduction. Hi, everyone. Thank you for joining us today. I will present our work on Megatron and training multi-billion transformer-based language models. Looking at the NLP research over the past couple of years, training largest transformer-based language model has been the best way to achieve the state-of-the-art in NLP applications. Great works such as BERT, GPT, and T5 has shown how this scale can help with some of the canonical NLP tasks, as well as recent, more research-oriented tasks, for example, end-to-end dialogue systems. Here, I am showing a plot of model size over time. As you can see, the growth has been exponential, meaning that the model size has increased by almost an order of magnitude every year. Extrapolating the current trend, by next year, the researchers will be training models close to 1 trillion parameter. So from the trends, it is clear that NLP research has its ImageNet moment and is moving towards larger and larger models. The paradigm of unsupervised pre-training on large text corpora and domain transfer to downstream tasks using fine-tuning on a small label dataset has eliminated the training dataset size issue. As a result of this, the NLP research requires algorithm, techniques, and tools to support training such large models. However, before we go through the details of how to do this and how to scale, I would like to take a few minutes and give some examples from Megatron on how large models can benefit NLP field. The first example is a left-to-right language model. The model is a GPT-2 based language model trained on 174 gigabytes of text from Reddit, Common Crawl stories, some news, and Wikipedia. On the right, I am showing the language model perplexity, which is a measure of how good the model can predict next word given the context. We see a monotonic decrease in perplexity as the model size increases. On the left, in the table, we look at zero-shot perplexity on a dataset that the model has not seen. Again, the same trend we observe, that perplexity goes down as the size increases and establishes new SOTA. So one question here is, how can we use such a model? These models, left-to-right language models, are great text generators. They can generate long, fluent, and coherent text. Here I will show you an example of such generations. As you can see on the screen, we provide a short prompt to the model and ask it to generate and complete the text. The prompt is about Greta Thunberg and her effort to increase awareness about global warming. Let's see what a Megatron 8.3 billion parameter model has to say about this. As you can see, the generated text is relevant, fluent, and coherent. It even brings Vice President Al Gore to the discussion. And also, at the end of the conversation, we see that model has generated an end of text, which means that the generation is done and it's finished. Moving to a more commonly used model, BERT, we observe similar trends on downstream task accuracies when we scale the model. Here we're showing the accuracy of different models on some canonical benchmarks such as MNLI, QQP, which is paraphrasing, Squad 1 and 2, which are question answering, and RACE, which is a reading comprehension task. As you can see, as the model size increases, the accuracy improves and establishes a state-of-the-art result. One other thing to note as well, larger model trained over fewer number of tokens produces better result. This is clear in the trained token column here. One question about these larger model is, yeah, great, larger models are better, but we cannot afford to have a 10 billion parameter BERT model, for example, in the production system and simultaneously serve 1 million query per second. So what's the benefit of these large models for production systems? So the answer, at least the answer that I have, is twofold. First, we and other teams, the community, is working on making inference more affordable. But more importantly, the use of these models is not just for inference. Here I show you the benefit. Here I'm going to show you a benefit of large model in a non-inference application mode. So what we do, we teach our model to generate question and answer pairs and use that to train a question answering model. So it's multiple steps. We do this in 4 steps basically. We use a large GPT model similar to what I showed in the previous to generate context unconditionally and generate the text. Then we use a BERT model to extract answer spans or answers from this synthetically generated text. Having the context and the answer, we use another GPT model to generate questions. And we over-generate questions because some of the question and answer pairs are not valid. And in the last step, we filter these question and answer that are not valid, resulting in a high-quality synthetic data. On the left side, I am showing the exact match and F1 accuracy of the synthetically generated data and compare it to human labeled trained model. As we can see, these cheaply generated cases or synthetic data surpasses the accuracy of the models used human labeled data. And the same trend again, this is not possible without using large models. On the left bottom, I'm showing the quality of the question generated as a function of the model size. As you can see, as the model size increases, the quality of these generations improve. One last, so how can we use these models in production or for some of the application? So here I'm showing question answering over a Tesla car manual. Basically, we give the model the Tesla car manual as the context and then try to ask questions about that. By the way, the reason that we chose Tesla car manual is my manager drives a Tesla and we wanted to make him excited. So let's see how our model does on the Tesla car manual. So the first question is about the battery for the key fob and what's the replacement battery. You can see that it gets the short and the long answer. The other one about the tire rotation and how many miles we should do that. And the model gets it right. So one last application that I would like to show here are the chatbots. So what we have done is we built a chatbot condition on previous conversation. In previous conversation, we used it as a way to control persona. We scaled this model up to 8.3 billion parameter model. And let's take a look at one example that is shown on the right with respect to the generation. So at the bottom, we see for a speaker B, the prior conversations that he has had with other speakers. At the top part of it, the speaker A and B start the conversation. This is as a prefix given to the model. And then in the second section, we two bots that one of them is A, one of them is B are talking to each other. One thing to notice is whenever the speaker B talks in the generated text, it actually follows the format. For example, this speaker uses lowercase for the word I, and as you can see, when the values are generated, it uses lowercase. As also in the previous conversation, the user mentions I'm a newbie, and here it says, oh, I just started playing in December 2018. The other thing is also it attend to the prior conversation, or it attend to the beginning of the conversation. For example, the speaker A uses 3ds in capital form versus speaker B uses in lower form. Whenever it generates something for speaker A, it actually uses capital as well. So I hope the discussion and application examples motivated enough the need for large NLP models. To empower this research, we need software and hardware that can efficiently and easily enable training such models. Megatron is our attempt to provide elements required to train such NLP models. Megatron is NVIDIA's framework for efficiently training the world's largest transformer-based language model. All the cases that I mentioned are trained using Megatron. Megatron was also been used by Microsoft to train Turing NLG with 17 billion parameter models. It has also influenced some of the development in the Blender bot by Facebook. So when we were designing Megatron, we had certain goals in mind. We wanted to have a low barrier to entry and the ability to build on top of our existing code base. We had both BERT and GPT code bases, well tested, and we only needed to scale them up. As a result, we aimed for designing simple methods that require minimal changes to existing code base, and it does not require rewriting code. Our goal was to target transformer-based language models at billions of parameters. We did not aim to build a generic framework that supports all sorts of parallelism and all sorts of networks. Also, being part of NVIDIA, it is important for us to achieve high utilization at large number of GPUs and make sure that the resources are used efficiently. So, as Paulius and other speakers pointed out, there are two forms of model parallelism. I'm not going to spend time here because you've already heard about them. There is intra-layer or pipeline parallelism, and then intra-layer or tensor parallelism. Tensor parallelism breaks the tensors basically along the y-axis, versus pipeline parallelism breaks it along the different layers, basically. So for Megatron, we chose to do intra-layer or tensor layer parallelism for several reasons. First and most importantly, it's simple to implement. For us, as NLP researcher, it's important, the simplicity is important. The parallelism is not the end, it's basically mean to an end, and end is basically training large and efficient and powerful language models. And as a result, it was important for us to choose methods that are very simple. Second, these models, intra-layer model parallelism is easier to do to load balance, especially for pipeline parallelism. The beginning and the end layers are typically a challenge. Also, tensor parallelism is less restrictive on the batch size. Pipeline parallelism has the bubble and needs to have several micro batches. However, I should also mention that intra-layer and inter-layer model parallelism are orthogonal. And for training very large models, these two approaches need to be used simultaneously at the same time. For example, GPT-3, OpenAI, for training GPT-3, they use both methods simultaneously. The other thing that helps us with tensor parallelism are transformers with their huge gems. And as a result, the mass intensity is not going to be an issue. I will touch base on this in the next slide. And last but not least, NVIDIA DGX box with NVLink. We know that tensor parallelism requires more communication and synchronization point, but when we have these NVLinks inside DGX A100 boxes at 600 gigabyte per second, it actually helps to reduce the latencies associated with communication. So I mentioned the mass intensity, so let's touch base on that. There are no parallelism comes without with no challenges, basically. There are two main challenges with respect to tensor parallelism. One is it results in lower mass intensity, and second, it has extra blocking communication needed. So let's take a look at a simple example. A matrix multiply y is equal to xa, and let's assume it's all a square. The A is split across its columns to p partitions. As we can see, the flops scale by linearly, but the bandwidth does not scale linearly. And as a result, the mass intensity goes down. An ampere A100 mass intensity is about 200. So we should make sure if we don't want to be memory bound, we need to have a mass intensity higher than this. And as a result, that's a challenge for the interlayer model parallelism. The other thing is also a touch base, is interlayer model parallelism requires more communication. However, the DGX-A100 with NVLink is our friend here. So let's take a look at the tensor parallelism for a simple case, y is equal to xa. I'm not going to spend a lot of time here as Paulius has gone through this. There are two ways of doing the parallelism. One is the row parallelism, the other one column parallelism. For example, column parallelism, we split it across its column. We need to add some communication primitives at the beginning and end of the computational graph for this. I'm not going to go through the details of it. But for example, F is an identity and then R reduce and back, or the identity in the forward and R reduce and backward. And then at the end, we have a G, which is an all gather in the forward and then a split in the backward. The same for, similar for row linear, for row parallel linear layers as well. So this was example for the column parallel. Again, the takeaway from here is we need to have these simple primitives inserted into the code to be able to parallelize these. So now the question is how we can do this for a transformer. So first of all, let's take a look at the transformer block. A transformer block, which shown in blue, consists of two other main blocks. One is a self-attention block, and then the other one is the MLP, which is two-layer feed-forward network in between having a GLU nonlinearity with a dropout. So we'll go through the details of this. But our approach for parallelizing these transformer is based on basically simplicity. So for us, simplicity is important, and we want to parallelize our code by insertion of few simple primitives such as if and g, as I explained in the previous slide. For these primitives, we rely on nickel and PyTorch, and we do not try to develop anything fancy in C. Our approach relies on grouping the mass-heavy operations as much as possible before we introduce a parallel communication point. Let's see how we can do this in the transformer. So as I mentioned, there are two main blocks, MLP and then self-attention. MLP is easier because it's just linear layer. Let's start with that. When we have an MLP consists of a matrix multiply, a GLU nonlinearity, again, another matrix multiply plus dropout. So if we do the first matrix multiply along, we split it A row-wise, basically, we end up y is equal to GLU of x1a1 plus x2a2. And if we want to calculate this GLU, then we need to introduce a communication point because GLU is nonlinear, so GLU of sum is not sum of the GLU. Versus if we do the column parallelism, or a split A along its column, you can see that we end up two disjoint partition that we can do GLU of the first partition and the second partition. So how can we take advantage of this for the whole MLP? So for the whole MLP, what we do is combining the row and column parallelism. Let's see how we do it. So here, the first block is a GLU of the XA. So we split A along its columns. X comes in, gets multiplied. We do the activation or nonlinearity, and then we have the parallel outputs, basically. Instead of introducing a synchronization point or a communication point, we parallelize B along its rows, and then we feed it directly. So we do these two multiplication, and then we need to have an R reduce, and then a dropout. So F is basically passed through in the forward, G is the R reduce in the forward, and then we have the dropout. Please note that we cannot replace the order of G and dropout, because dropout of sum is not sum of the dropout. So F and G's are very simple here. So with this system, we can incorporate or insert F and G. F and G are conjugate. F is identity in the forward, is R reduce in the backward, and G is R reduce in forward and identity in backward. I mentioned F and G are simple. Let's look at just implementation for F. For example, for F, we extend the torch autograph In the forward, we do a pass-through. In the backward, we do R-reduce. G is basically the forward, backward of this method is replaced. How can we do the self-attention partitioning? So for self-attention, we use the same approach as was used as mesh TensorFlow. We basically parallelize across attention head. We have the key query values, and they are replicated for different, or they have been extended for different attention heads. So we basically break and put some of the attention head for one GPU, the other attention head to the other GPUs, or however number of GPUs that you might have. So let's see in details how this is done. So here again, we have the same F and G. So F comes in here. We have bunch of a query key and value associated with the first set of attention head. And then we have key query value to the second attention head. This is basically similar to partitioning along the columns of the matrix. We do the operation. We skip the sync point. We partition the linear layer at the end of the attention head along its rows, and then we can directly do the matrix multiply. We have the G and the dropout. So these are the same F and Gs that were defined for the MLP as well. So in summary, a transformer block will have both serial and parallel regions. It will have layer norms and dropouts in serial region versus there are two parallel regions. One is the self-attention with two R-reduces, one in forward, one in backward. The same for the MLP. It will have two R-reduces, one in forward and one in backward. So this was for the model parallelism. We know that for all the applications of deep learning, we need to be able to do data parallelism as well. And data parallelism is very straightforward. We can just do the communication between the groups that include the model themselves as well. So I'm not going to go through the details of the incorporation of the data parallelism. So let's look at, we mentioned we want to do it efficiently. So let's look at how efficient our implementation is. Here we're looking at weak scaling efficiency on our DGX-A100 SuperPod cluster Selene. I'm looking at 4 different cases of 1 billion, 2 billion, 4 billion, and 8 billion parameters. And they run on 1-way model parallel, 2, 4, and 8-way model parallel. We have also introduced 128-way data parallelism, which results into usage of 128, 256, all the way up to 1,000 GPUs. All of these numbers are compared to the single GPU of 1.2 billion parameter case. So it's very strict and strong. And this case is also achieves a good utilization. It achieves 118 teraflops per second on an Ampere A100, which is 38% of the peak theoretical flop. Here is, again, this is the flops for end-to-end. So we include all the data loading, all other pieces as well. As you can see, the model parallel efficiency drops, but only by 20%, and even 8-way model parallel still runs at 80% efficiency. When we scale it to up to 1024 GPUs, we see like 78.9. And as you can see, is also our efficiency drop for the model parallel versus model plus data parallel is minimal. The reason here is we use overlapping of backpropagation with R-reduced communications as well. So great. We devised a method to scale transformer-based model, and we showed great scaling and utilization. So are we done? Meaning that we just can put it on our cluster and scale it? Well, this is typically not the case, and other details needs to be taken into account. So I will give you a few examples of the issues we encountered that we needed to resolve before scaling these models. First is the BERT example that I showed. So this BERT was developed by Delvin et al. And we originally used the exact architecture that they used. And so we had they scaled it up to 336 million parameters, and we tried to scale the model by a factor of 2 and could not train the model. Here, as I'm showing a language model loss curve as a number of iteration, For the 336 million, we see that everything is looking good, but when we scale that model to 752 million, the loss becomes unstable and requires changes. We looked deeper into the structure of the network and found that the residual connection needs to be rearranged for the gradients to flow directly into the network without going through the layer norm. Here, the case A is the original implementation. The case B is basically rearrangement of these residual connection. And as you can see that when we rearrange the residual connection, the loss decreases and we get really good looking loss as well. One more note here: when we rearrange rearrange the residual connections, we needed to change the initialization for some of these weight matrices as well to account for the excessive gradient that flows through. The other thing that we needed to pay careful attention with random numbers. Random numbers are essential and critical in deep learning because of initialization, because of dropout, because of sampling and other things. And reproducibility is also important. But tensor parallelism introduces a challenge for random numbers. Let's look at the block here, which is the self-attention plus the dropout. And if we look and zoom in details, we see that we have two forms of dropout. One is dropout after the softmax, and then dropout at the end of the layer. This dropout is serial and it needs to be the same on all GPUs, versus this one should be different on model parallel GPUs. So as a result, we need to track two different RNGs and switch between these two whenever, and need to know like where we are and incorporate them. So this is actually critical, otherwise we will end up symmetry with the system as well. So one last aspect that I would like to touch base are also data loaders. So let's take a look at what was our challenge with data loaders. So data loaders, here I'm showing on the left. On the right, I am showing the plot of the loss curve as the number of iteration for a GPT-2 model. At the top, we have two sort of shuffling for the data loader. One is at the end of each epoch, and then the other one at the global shuffling. So when we do a 345 million parameter model, the epoch shuffling, the curves are very smooth, nothing goes wrong, everything is good. Versus when we scale that with the same data loader to 8.3 billion, we see that there are actually kinks at the boundary of the epochs. And so these models are a lot more powerful and have more capacity to memorize. When we switch that to a global shuffle, we see that these kinks go away and the curve and the loss curve becomes very smooth. So I would like to leave you with the summary and the conclusion and open the floor for any questions. Thank you.
Okay. Thank you, Mohammed. We have a few questions on the Slack channel and not a lot of time, so let me start right away. So a question from Shin Wang. He's asking about the scaling factor and efficiency if only data parallel distribution were used. I guess the question is, how would data parallel only compare efficiency-wise to combining data parallel and model parallel for training Megatron? Oh, Mohammed, do you get a question feed? Okay, please hang on a sec. We're dealing with some technical issues we'll resolve in a moment. Okay. All right, so we have time for one question. So let me try that. We have a question on comparing.
Yeah, that's a.
Yep, go ahead.
Sure. Yeah, that's a very good question. So one thing that we actually didn't do this scaling in isolation, but you can deduce it from the slides comparing. Yes. I am on the question feed. Hello?
Okay.
Okay.
I think by now we're out of time, so I think it's probably best to take to the Slack channel and complete the sort of the QA section there, and I think we'll move on to the next talk. All right. Yep. Please join me in thanking Mohammed, and we'll move on to the next talk. So our next presenter is Weiji Zhao from Baidu Research USA. At Baidu, Weiji investigates problems in scalable machine learning systems, such as neural network training, approximate neural neighbor search, as well as scientific data processing and database systems. Weiji holds a PhD from University of California, Merced. So Weiji, please take it away.
Nice to have a talk in Hot Chips. So my topic is the distributed premier server for massive ad system. And this is joint work with 德平谢、荣来甲、玉垒前、瑞全丁、明明孙, and Ping Li. So let's begin with the sponsored online advertising. When you search some keywords in a search engine, say you want to search Palo Alto Hotel, then definitely the first several search results you get will be some ads. And the search engine want to publish and display some ads that is relevant to your query, and also that's relevant to the user. They want the user to click that ads. So one very important metric of the sponsored online advertising is called click-through rate. Here, click-through rate, we call it CTR. It equals the number of click-throughs divided by the number of impressions. Here, the number of impressions means how many times an ad is displayed. Okay, so we have some inputs, like for a given ad, for a query for the given user, we want to predict what the probability the user will click that given ad. So we can see the input is a query, say just the keywords we just entered in the box. It can be like a word embedding of those keywords. And we have an ad, like the embedding of the ad features. And we can also have some inputs like the user portrait containing something like the gender of the user, the geographical information of the users. With those many things, we usually have a high dimensional sparse factor. Here, the sparse, it is very sparse because those inputs are encoded in a one-hot fashion. We have a huge sparse input factor, which has up to 10 to the 11 dimensions, because you have many words, some several things, and consider you have a super long binary vector and only having several hundreds of non-zeros. Say if one word, one position in that vector, one dimension in that vector represents a given word, then you have a super large dictionary, then it can be a high dimensional case. And also we have many features that's in that case, we have the 10 to the 11 dimensions. The good news is we only have several hundreds of non-zeros in this super high dimensional vector. Okay, remember this, and we will use that later. We have a high dimensional sparse vector, and we want to use a model, say neural network, to predict the click-through rate. Let's review the CTR prediction models we have used at Baidu. So From 2009 and earlier, we used single machine CTI models. And in 2010, distributed logistic regressions and distributed primary servers are introduced. From 2013, we start to use the distributed deep neural networks with extremely large models. And since 2017, we introduced a single GPU AI box and multi-GPU hierarchical primary server. Approximate nearest neighbor search and maximum inner product search techniques are also used in this pipeline. Consider our CTI models are designed to predict, like, given an ad and all those user query features, we want to predict the CTR. But we cannot enumerate all those ads and try to see whether this ad is good or whether that ad is good. Enumerate all those tons of ads in the large pool. We need to use those approximate nearest neighbor search and maximum inner product search technique to return a small collection of ads that is interesting to the user in a coarse granularity. And then we can apply our fine granularity CTI model, say the complicated deep neural networks, to do a final ranking. So the ANN and MIPS have become increasingly important in the whole pipeline of CTI prediction due to the popularity and maturity of embedding learning and improved ANN MIPS techniques. Okay, so we first use those approximate nearest neighbor search technique to get a small subset. Then we will apply the CTI prediction model on all those candidates. Here is a visual illustration of CTI models. Consider we have sparse inputs. As we said, we have 10 to the 11 dimensions. And first, the sparse input goes to an embedding layer. After that, we will have several fully connected layers. The embedding layer will embed our super high dimensional vector to a low dimensional representation, say several hundreds of dimensions. So the number of neurons in the fully connected layers are not that large, will be around 1 gigabyte. And for the embedding layer, since we have such a large dimensions, 10 to 11, we will have several parameters for each dimension. That means our embedding layer will be super large and can be as large as 10 terabytes. So in order to train this 10 terabyte model, we previously we used an MPI cluster solution, also known as the distributed primary server. Consider we have those large models that are out of one single machine's memory, and we partition all the parameters across the nodes in the cluster. We call them global parameter shards, and they are just distributed in the memory of each node. And for a worker thread, it will get some training examples from the network file system. And then it will figure out the required parameters and pull those parameters from the distributed primary server. After that, it has the parameters, has the training data. You can do the feed forward and backward propagation. After we have the gradients, we will push the gradients to the global primary server to update those parameters. Okay, this is our MPI cluster solution. It looks like not so fast since we have pretty much communications. But we have to do this since we need to put all those parameters in the memory, and we need many machines, there are CPUs to do the training computations. But there's a very straightforward question is, why do we need such a massive model? Why do we need that 10 to the 11 number of dimensions. Can we just simply reduce the model size? Like we can shrink our inputs from 10 to the 11 to some smaller number. Then we just need to do some simple things of that. We can train it on a single machine, right? So we have tried that. We do the hashing for reducing the CTI models. The hashing function we use is called one permutation plus one sign random projection. Here is an example on the image search as datasets, and it is typically a small source of revenue. We can see that for the base logistic regression solution and the base deep neural network solution, we will have similar number of non-zero weights here. There are around like 32 billion non-zero parameters. And we can see that there is somehow a large gap, more than 3% between the test AUC of baseline logistic regression and baseline deep neural network. When we try to hashing the inputs, say we will hash it to k bits. Say when the k is as large as 2 to the 34, we can reduce our number of parameters to around 20%. With somehow similar test AUC and also has significantly improvements over the baseline logistic regression. Although there is still a 0.7% difference between DNN, but we can claim that hashing plus DNN can significantly improve over the logistic regression and somehow close to the DNN. It will be a fine solution if our goal is to use single machine to achieve good accuracy. And let's see another example. So web search ads use more features and larger models. Here we can see that the number of non-zero weights for the baseline logistic regression and deep neural network goes to around 200 billion. In this case, even though we perform the hash to 2 to the 32 bits, we still cannot catch up with the test AUC of baseline DNN. And even bad news is a 0.1 decrease in AUC would result in a noticeable decrease in revenue. That is not tolerable. And solution of using hashing plus DNN plus single machine is, hello? Okay, so the solution of using hashing plus DNN plus single machine is typically not acceptable here, since although we can slightly improve over the baseline logistic regression, but we are still more than 1% off than the DNN. Also, the AUC is very important here. We don't want to hash the inputs, just want to make the training fast, but we have to guarantee the prediction accuracy. Okay, now we know that we must use this massive model, the 10 terabyte model parameters. That means to train this massive model, we need to use hundreds of computing nodes. When we use hundreds of computing nodes, we will have high hardware and maintenance costs since we have a large cluster to maintain. And we will have a high communication cost because we have hundreds of nodes and we need to frequently do this distributed parameter server push and pull. That will be time consuming. So one thing is people are always using GPUs or other hard chips to train those models. Can we just train our 10 terabyte model with GPUs? This somehow sounds crazy because we need to hold this 10 terabyte parameters in GPU. However, even the largest GPU, the GPU memory we can bus is something like 32 gigabytes or 40 gigabytes. So how can we hold these 10 terabyte parameters in GPU? Without storing these things in the GPU, we cannot let GPU do the training. So the good news is, remember that although our input vector is very high dimensional, but we only have a few hundreds of non-zeros per training example. That means only a small subset of parameters in the embedding layer is used and updated in a batch. In this case, we can know that the working parameters that can actually be held in the GPU high bandwidth memory. Then we can solve this massive scale machine learning problem in a system way. So we propose a hierarchical parameter server that has 3 layers. The first layer is called HBM parameter server. HBM is the memory of GPU. So the working parameters are stored in the HBM, and those GPUs can do inter-GPU communications on within the GPUs in the same machine, and can also do RDMA remote synchronization with the GPU on other machines in the cluster. And for those parameters that cannot be stored in GPU memory, we have a memory parameter server that is just located in the main memory of each machine. Also, since we have 10 terabytes, 10 terabyte parameters, even the memory may not be large enough to hold everything. So we also have a SSD parameter server that store the materialized parameters as files, and it's something it can. Our memory parameter server acts like a faster cache of the SSD PS, and something our HBM parameter server acts as a fast cache of memory parameter server. So let's see a concrete example. Consider we have 2 nodes here, and say all the parameters with the odd ID are stored on the node 1, and all the parameters with the even ID are stored on node 2. So we have 4 training mini batch, and say we first identify the working parameters. It can be the union of all the required parameters in each training mini batches. After that, our memory parameter server will pull the required parameters from its own local memory parameter server or the local SSD parameter server. And for those parameters are not located on the current machine, we will initiate a remote pull request to other memory parameter server. After that, all the working parameters are in the memory now. We will partition these parameters to each GPU on this machine, and say GPU 1 gets 4, 5, 11, and 50, those 4 parameters, and GPU 2 gets the other. Say the mini batch 1 is assigned to the GPU 1 worker 1, and it will pull its local HBM parameter server and remote HBM parameter server to get the required parameters for this mini batch. After that, GPU 1 worker 1 has already got everything it needs to perform the training, and we can do the feed forward and backward propagation. So we have introduced a lot of optimizations for the hierarchical parameter server. And here I will just introduce one very interesting thing. Other optimizations can be found in these 2 papers. So Bloom filter is a probabilistic data structure that will tell us whether a parameter exists in a collection, or a parameter does not exist in a collection. So Bloom filter only requires a sublinear memory footprint, so it is very small. And when we ask the Bloom filter whether a parameter exists, it has 2 kinds of answer. One is the parameter may exist, or the parameter is definitely not is not existing in the collection. So with this property, we can attach a Bloom filter between the SSD primary server and the memory primary server. Consider we have so many training parameters. However, we only have a few hundreds of non-zeros per training example. That means in the beginning of the training, those parameters, many parameters are not updated at all. So we just try to get some parameters from the SSD. And what we get is just an initial value, since nobody has updated that since before. In this case, we can ask our Bloom filter first, whether this parameter is updated or not. If the Bloom filter tells us the parameter is definitely not updated before, that means even though we go to the SSD, we are just getting initialized value. So we can just initialize that parameter in the memory without touching the SSD at all, if the Bloom filter tells us the parameter is not updated before. So in this case, with the Bloom filter, we can significantly reduce the SSD I/O, since we just need to generate a random number in the memory as the parameter value. With this optimization, we can make our SSD, the latency of SSD somehow catch up with our training speed. Okay, let's see some experimental evaluation results. We do our experiments on 4 GPU computing nodes. Each node has 8 cutting edge 32 gigabytes HBM GPUs, server grade CPUs with 48 cores, around 1 terabyte of memory, around 20 terabytes RAID 0 NVMe SSDs, and 100 GB RDMA network adapter. We do the test on 5 real CTR models and real data. We call them A, B, C, D, and E. The column of non-zeros means the number of non-zeros per training example. Here, this column, number of sparse, means the number of dimensions for each sparse input. And here, the number of dense means the number of neurons for the following fully connected layers. And this is the size of our models. The size varies from 300 gigabytes to 10 terabytes. And okay, here the MPI column is the number of machines we use in the production line. We can see that the execution time of our 4-node hierarchical primary server is like 2 times better than hundreds of MPI cluster solutions. So people can also ask that your GPU use so many fancy hardware, that means it can be very expensive. Of course, we can normalize the speed up with the hardware and maintenance costs. Say 1 GPU node is somehow comparable with the cost of 10 CPU only nodes. And that means we are comparing with 4 GPU nodes with 75 to 150 CPU nodes, and we are 2 times faster. If we use the cost normalized speed up, you can see that for large models, our solution is 8.3 to 9.0 times faster, because we are using 4 GPU nodes to beat hundreds of CPU nodes. Of course, we just said AUC is very important, and we can see that the test accuracy is somehow unchanged, and our 4 nodes hierarchical primary server is somehow scalable. It achieves almost ideal scale, ideal linear speed up here. And finally, let's conclude this talk. Here we introduce the architecture of a distributed GPU primary server for massive deep learning ad systems. And we perform extensive sets of experiments on 5 CTR prediction models. Our 4-node hierarchical GPU model is more than 2 times faster than 150 nodes in memory distributed primary servers. So since time is up, let's just see whether there are any questions.
Thank you, Wei-Ji. We have a few questions on the channel. So I'll start with a question from, and I hope I don't destroy the name too badly, Tianchi Tang. So you commented that this is a very interesting system. Is there a similar setup for inference or serving?
The serving part is pretty easy since we just need to go through all these things. It is very similar to the training part, so actually the same, but we don't need so many computing parts.
Okay.
So that means we can use less nodes.
Okay. We have a question from Cliff Young. So he's wondering if you could elaborate a little bit more about the embedding table size, how it gets to 10 terabytes of storage. So is that, let's say, 100 columns per table and 100 billion entries, or some other dimensions?
Excuse me, I didn't hear the question well.
Oh,
so
I'm sorry.
Your voice is very low in my earphone.
Hopefully it's better now.
Yes.
Excellent. We have a question from Cliff Young, who is wondering about a few more details on the embedding size. Effectively, how does one get to 10 terabytes? What is the latent space dimensionality? So is it, let's say, 100 elements per embedding vector and 100 billion rows in embeddings, or some other breakdown of that 10 terabytes?
Yes, something like that. It is like the embedding layer has like several hundreds of dimensions, and then it will be the several hundred times the 10 to the 11.
Okay, thank you. We have a question on hashing. So effectively, how does hashing reduce embedding table size? What is the principle behind that?
I see. The case of hashing is we can hash the original sparse vector to several bits. Like for the hashing is when we apply one hashing, we will get one binary bits. And if we do this independently k times, we will get 10 bits, k bits. After that, we just reduce our massive input dimension to just a k bit dense vector.
Okay. So we have a few questions in the channel related to embeddings. I'll try to maybe paraphrase them or put them through my filter. So you mentioned that you are doing several hundred lookups in the embedding tables per sample. So I was wondering if those are effectively one-hot lookups that then somehow have to be interacted, or there's some form of multi-hot lookup where you will look up several entries, but then point once combine them before passing them to the MLP.
I didn't really get the question clearly. So I think it is something like the multi-hot part, and also since we have the inputs come from various sources, and all of them will have some non-zero part, and we need to retrieve it for the embedding table.
Okay, thank you. We actually have another question on embedding table sizes. So Xiaoyuma is wondering whether you think that embedding tables will continue to grow in the future and get even larger.
Yeah, definitely. And in our experiences, with higher dimensional embeddings, you will get slightly better performance. As far as our computational power can catch up, I believe large embedding size will matter a lot.
Great. I think we are out of time for this session. So I think we'll stop now. So please join me in thanking Wei-Ji. And we will continue to the last session that's part of this tutorial, and there'll be another tutorial on quantum computing afterwards, so please stay on for that. So let me switch over here. So our next speaker is Zhifeng Chen from Google Brain, where he's a principal engineer. Since joining the Google Brain team, he has worked on a number of deep learning projects, including TensorFlow, neural machine translation, speech recognition, and speech generation. His most recent projects, GPipe and GShard, focus on scalable software to support training large models in model parallel fashion on large-scale systems. And before Google Brain, he focused on distributed large-scale systems such as Bigtable, Gmail, and Zanzibar. So with that, Zhifeng, please take it away.
Hi, this is Zhifeng Chen from Google. I will talk about GShard today. GShard is a system we built to scale large machine learning models. It allowed us to build and explore giant neural networks for multilingual machine translation. We explored models with more than 1 trillion parameters. In this talk, we would like to share with you our experience and the thoughts we had while we worked on the project. It's a joint with Dima, HJ, Yuanzhong, Dehao, Ohan, Yanping, Maxime, and Norm. The work is supported by many other colleagues throughout Google, Google Research, and Google Brain teams. In the last few years, we saw many efforts to create very big neural nets for natural language understanding problems. GShard models are these 3 red circles in the figure. In this talk, I will try to explain what motivated us to pursue building these models, what kind of architectures these models use, what software we built to enable building these models, and I'll show some results from these models. GShard is motivated by Google Translate. Since 2016, the core model of Google Translate has been always neural sequence-to-sequence models. For years, the mission of Google Translate has always been to develop a universal machine translation model for as many languages as many domains as possible. The goal can trace back to 1950s when computational linguistics as an interdisciplinary field started. To further advance machine translation, Google Translate's production and research teams faced many challenges. First of all, the training data set is very large. Today, these models are trained with more than 25 billion sentence pairs across many languages. Languages with high resources, such as Spanish, French, and German, typically have hundreds of millions of sentence pairs. On the other hand, the training data distribution of different languages is very uneven. Low resources languages may have 4 magnitudes fewer training data available than those available to high resources languages. Google Translate supports around 100 languages today. We want to increase the language coverage. However, there are 1 or 2 magnitudes more human languages existing today in the world than we currently can support. So it's still a long way to go. It follows natural for us to seek for a model that can generalize very well. We hope the model can generalize from observed data to unobserved data, from high-resource languages to low-resource languages, and maybe the model can eventually generalize to human languages that have almost no digitized data. Think about those ancient Egyptian languages that no modern people can speak. To generalize well, the usual thinking is that the model needs to be able to learn from as much as data as possible. Ideally, the model should be in the irreducible error regime in this figure, where the mistakes a model makes is indistinguishable from white noises. ML researchers generally believe most practical problems are in the middle of this curve. That is to say, in many cases, the model is not powerful enough yet to fit well the data. This is particularly true for machine translation, as we observed in practice. We never saw a model that is able to overfit the large amount of training data we feed to it. So it's always on our mind to scale up the model. We call this scaling effort M4, which stands for Massive Multilingual Machine Translation Model. M4 as a research agenda covers many research problems. It develops better multitasking learning to learn many languages in a single model. It develops techniques to address imbalance in the training data. It also drives many efforts in improving model trainability, optimization, and efficiency. This talk focuses on how G-Shard helped the M4 project to increase its neural network capacity to a new level never done before. Model capacity is a vague term. An easy approximation is to measure the number of parameters a model has. If we look at this metric, it is often compared to the number of synapses animal brains have. The number of synapses an animal brain has varied widely. It ranges from 1 million to 1 quadrillion, that is 10 to the power of 15. It could be interesting and exciting to see how our field has evolved so quickly along this dimension in the last few years. In 2015, the models reported in the original ResNet and the Button Attention paper contained about tens of millions parameters. In 2016, the seek-to-seek model used in Google Translation production was about 1 magnitude larger. It was about 200 million parameters. By 2017, the original transformer model contained about 400 million parameters. In the following 2 years, we saw several reported models reach the range of several billions of parameters or even tens of billions of parameters. This year, we saw GPT-3 and G-Shard models are now contains hundreds of billions or even trillions of parameters now. It is pretty amazing to see how fast neural nets have been scaled up along this dimension in recent years, as evident in either pure language modeling or seek-to-seek models such as those for machine translations. Scaling up nets have brought real model quality improvements, and the trend does seem to continue. If we continue marching along this metric, and if we can scale up another 3 magnitudes, a neural net will have as many as synapses as a human brain has. I'm rather curious to see what amazing things such a large model will be able to do. It is probably worthwhile to reflect what we have learned in our scaling efforts, and maybe some lessons we learned can give us hints and guidances as for how to scale further. Building a giant neural net needs to consider many factors together. From the application side, for example, the machine translation will understand the desire to process big datasets and solve multiple tasks in a single model. We are also very fortunate to live in a time where the computation horsepower is readily available to us, GPUs, TPUs, fancy networks, etc. But to put this together to solve the problem, we find that it still took quite a bit of effort to choose the right neural net architecture which can effectively leverage the hardware. We also have to think hard about how to manage the software development complexity to support effective collaboration among system engineers and model researchers. The collaboration allows system engineers to focus on system problems, that is, how to best use the giant parallel machines we are given to train the model. Meanwhile, model researchers are largely detached from the details, such as system runtime, compiler, accelerator, hardware, etc. In our G-Shard work, we found that sparsely gated transformer models are very effective in increasing neural net capacities at this scale, and the resulting models fit very well with our parallel hardware TPU pods for training. We achieved, to some degrees, pretty decent separation of concerns of modeling and runtime. The majority of the model is written in the standard TensorFlow code. After the model is written, only a few annotations on some tensors are needed for the programmer to express their parallelization intention. These parallelization intentions are then passed down to the underlying runtime and the compiler to come up with the optimized parallel plans for execution. G-Shard models are transformer-based models. Transformer was proposed in the 2017 Attention is All You Need paper. It is very powerful in modeling sequence problems. It is now an indispensable tool in deep learning toolbox. Right now, many SOTA results in NLP domains, for example in machine translation or in speech recognition, etc., are based on transformer models. Here we show a transformer layer used in the encoder. The corresponding layer in the decoder has an extra masking, but otherwise it's very similar. Each layer takes a 3D tensor representing a batch of sequences of inputs. Each transformer applies the multi-headed self-attention on the input sequence first, then applies a feed-forward network before the output. These 2 steps are connected with residual connections and layer normalizations. At this level of details, The math is very simple. The attention and the feed-forward part can be easily written using a few einsums, softmax, and some element-wise functions. If we compare transformer models to recurrent nets, which is another very dominant way of modeling sequence problems, one can immediately see the implementation of transformer models does not need any loop structures. This property made the model researcher's life much easier. More relevant here is that this kind of model structure is very friendly to automatic compiler infrastructure to parallelize the program. One can directly make a transformer model bigger in two ways. One is to make it deeper, stacking more layers. The other is to make each layer wider. Each layer has two parameters to control how wide each layer is: the model dimension and the hidden dimension. The number of parameters of each transformer layer is linear to the product of these two parameters. However, one major downside of simply scaling up a model this way is the computation costs also increase linear to the number of parameters. Our early project GPipe and many other efforts all reported the significant longer training time when simply scaling up models this way. In GSHA model, we took a different approach. We adopted an idea proposed in another 2017 paper, Outrageously Large Neural Networks, namely the sparsely gated mixture of experts layer. For short, we call this layer a MOE layer. An MOE layer has a very unique subcomponent called the gating function, which is a neural net. The gating function takes an input vector and makes a routing decision for the input vector. The input vector is then given to one of n experts. Each expert is in turn an independent neural net. Such a layer has two important desirable properties. First, each input only activates one small part of the layer. That means the cost of training and inference of this model is not strongly correlated with the model size. Second, because experts are independent of each other, this model structure is embarrassingly easy for parallelization. We can freely partition the experts and don't worry much about data exchange between these experts. The original MOE was tested with recurrent nets. In GSHA, we use it simply with transformer layers. It's actually pretty straightforward because the basic transformer has a feed-forward network after the attention. It's natural for us just to replace it with MOE layer. In our experiments, we only injected the MOE layer into every other transformer layer in the encoder stack. We don't have a specific reason for why not replace every feed-forward network with MOE in the whole stack. That might also just work. Let us dig just a little bit into the details here. I promise that's the only equations of this work. In our setup, each expert is a two-layer feed-forward network with ReLU activations. The MOE layer has many experts. We experiment up to 2048 experts. The gating function is relatively complicated in its internal logic. Its interface is rather easy to understand. For each input vector, the gating function returns a sparse vector. That is, most elements in the return vector are zeros. In our setup, there are at most two elements are non-zeros, and the corresponding experts are given the input vector. The layer's output is the weighted sum of this expert's output for this input. During training, each step contains lots of tokens. The above computation is adjusted to be batch-oriented, in that the gating function outputs are combined into a very big sparse tensor G, and it represents the routing table for all the tokens. The routing table G is clearly very sparse. However, it later becomes pretty nice in the implementation and is appropriate for parallelized execution on our hardware. The gating function's logic is rather simple if expressed in terms of a single input, but we needed its implementation to be batch-friendly. We manually wrote it purely in the linear algebra way. The process is pretty subtle and painful, but doable overall. It might be possible that in some recent framework, for example JAX, we could automatically convert this piece of logic into batch-oriented implementation without much manual work. The gating function is also designed to balance the load, the number of tokens each expert needs to handle during a big batch training. We used an auxiliary loss to encourage the routing decisions to be balanced. There are quite a bit other algorithm-related details to make the model work in practice. at the scale we are working at. If you're interested, please refer to our technical report for more details. The standard transformer models are trained using data parallelism. That is, you have n devices, say 48 compute devices. We stamp out the whole model n times. Every device has all the parameters during training. Each device independently reads the training data and computes the gradient for the parameters. Then all gradients are all reduced and the parameters on every device got updated in the same way. A pure data parallelism approach does not work for G-shot MOE models because the whole model has many MOE layers and each MOE layer has thousands of experts. So each MOE layer ends up with tens of billions of parameters. So intuitively, for MOE layers, we want the parameters to be spread or sharded to many devices and moves the activation tensor to the parameters. In the same time, we keep the other layers replicated as in the data parallelism. This leads to an interesting software problem. We want to express the intent of parallelizing the whole model in a hybrid mode. Some parts are replicated and some parts are sharded. What kind of abstraction should we use here? It should be convenient to be used by our model writers, while the system software should get enough information to generate the parallel programs. G-shot can be viewed as one attempt we did trying to answer the question. In our development environment, Lingvo is the high-level framework we use for several years developing production-level quality models. Over the years, we have already accumulated a large set of building blocks for building neural nets. TensorFlow is the ML framework underlying Lingvo. These Python frameworks are used by our production model developers and researchers, so we want to use these libraries as much as possible. G-shot introduced some high-level lightweight annotation in the Python user program, which I will talk about more in a later slide. These annotations are passed to the lower software layers, particularly the XL compiler. We developed an extension in the compiler called SPMD Partitioner, which takes these sharding annotations and transforms related operations into sharded version. Note that users only need to annotate some tensors in the computation graph, and the compiler propagates the annotations forward and backwards to ensure all tensors are sharded properly. The SPMD partitioner also needs to manage to arrange data transfers by inserting various communication primitives. For example, if one tensor is sharded one way as an output of an operation, and its consuming operation specifies another sharding, the partitioner will use all-to-all or all-gather to reshuffle the tensor data. The sharding annotation can interact with other compiler tasks such as operation fusion or memory management, but the Excel compiler does its best to optimize for overall performance. We feel this arrangement is pretty effective in practice for us to hide unnecessary low-level system details from the model writers. Before I show an example code snippet in our model implementation, let us have a small recap of the Einstein operator. Einstein notation is a powerful and elegant way to express many complex tensor multidimensional arrays operations. The notion is essentially a tiny domain-specific language. It allows the programmer to specify on the spot a name, just a single letter, to each dimension of tensors involved in the computation, both input tensors and the output tensor. Then the equation specifies the logic, how the multiplication, addition, summation are applied to various dimensions. For example, here M0 has two dimensions, I and j, and M1 has two dimensions, j and k. We want the output tensor to have also two dimensions, I and k. In the end, we get O-plane matrix multiplication here. Einstein can also express lots of plane data movement operations. For example, the second line illustrates how a simple transpose is done on a matrix using an Einstein. Extensive usage of Einstein notations is critical to G-shot. It simplified lots of high-level Python code and allowed model researchers and system engineers to work together and understand each other better. It also turned out to be an important abstraction, very appropriate for the parallelizing compiler to work with. There are relatively few number of cases for our SPMD partitioner to take care and optimize. Here is the code snippet showing the core of the MOE layer to route inputs to experts. Line 2, 4, and 10 are lines adding G-shard annotations. Split used on line 2 and 10, it specifies the intention to shard respective tensors along the first dimension over D devices. The example here only split tensors along one dimension for simplicity. G-shard also supports splitting tensors along multiple dimensions in more demanding scenarios. Replicated used on line 4 specifies that tensor WG, which is the gating softmax weight matrix, is to be replicated. Top to gating on line 6 is calling another subroutine written in the standard TensorFlow code. The rest is just a few isoms doing the heavy lifting work. Note that the notation is sporadic throughout the code. We rely on the Excel partitioner path to reason about the shardings for unspecified tensors. For example, this patch mask in the code has no direct sharding annotations. The partitioner can derive that this patch mask is sharded along the first dimension because inputs are sharded along first dimensions. WG is replicated, and the internal logics of top to gating eventually emits tensors with first dimension sharded. The partition algorithm takes the above annotation and its automatic derived implicit sharding specification, and then emits per partition operations connected with cross-devices communication primitives to get a high-level computation done. For example, here's one example for a very basic sharded matrix multiplication. The first operand is sharded along the column dimension, and the second operand is sharded along the row dimensions. For simplicity, here we assume there are 4 devices, and both operands are sharded evenly and nicely over 4 devices. In this case, the partitioner instructs each device to run exactly the same program, a matmul, on its local data, then order reduce across these 4 devices to sum them up. You can imagine there are many more details to be taken care of. For example, shards can be imbalanced, in which case we may need to do an OR gather before computing the partial results. Here is one slightly more sophisticated example, which exists in the code snippet I showed earlier. The first operand is the routing dispatch tensor, and the second operand is the input vectors. The output tensor specifies the input to every expert. So it's more complex because the input tensors are sharded essentially along the batch dimension, but the output of this isom is sharded along another expert dimension, which is different from the inputs. That implies a reshard is needed. In this case, the partitioner will arrange an alt-wall after local dots are done. I'd like to note that the partitioner supports convolutions, even though our MT models do not use convolutions. If interested, please refer to our tech reports for how that is supported. We used the G-shard to train a family of multilingual machine translation models. We varied the number of experts and the number of layers, and the largest model we trained contained 1.1 trillion parameters. So far, we can reliably train models as large as 600 billion parameters to final convergence. This figure shows how this model improved the machine translation quality in terms of BLEU scores across all supported languages. The baseline model we compared against is non-MOE standard MT model used in Google Translation production. Each it has about 400 million parameters. Note that the baseline is actually composed of 100 models, one for each languages. The general observation from these models is that the bigger model does better, even when the model is as large as 600 billion. The average BLEU score improvement is very significant. Particularly, the long-tail, low-resource languages get more improvements. We hypothesize that the effect of transfer learning from high-resource languages to low-resource ones is more profound in these giant models. When we worked on scaling up neural nets, the training cost is always a big concern. That's also the reason motivated us to look for a better model that's more cost-effective than simply scaling dense models naively. This figure shows both wall time and overall computation cost of training G-shard MOE models. First, training 16 times larger model is actually faster in the wall time term. It took 2 weeks to train a 37 billion parameter model, while it only took 5 days to train a 600 billion parameter model. Second, the overall cost in terms of the wall time times number of devices used grows sublinearly in training G-sharp models. It takes 6 TPU core years to train a 37 billion model, while it only takes about 22 TPU core years to train the 600 billion models, which is 16 times larger. Overall, our experience tells us that sparsely gated networks, such as this MOE model, is practical to train super large models with high quality and low cost. One may also wonder whether G-sharp MOE model can scale further and what will prevent it to do so. Our roofline analysis hinted that the all-to-all latency can potentially be the bottleneck down the road. Recall that the routing of tokens incurs one all-to-all. On the TPU pod network, the latency of an all-to-all grows to according to the square root of the total number of devices. Our measurement confirms this analysis. We expect future hardware improvements in the interconnect area can alleviate this bottleneck. And as we have shown, innovations in the model architecture may also lead to approaches that enable scale up the models further while avoiding the hardware limitation today. In summary, G-sharp has shown that giant neural nets can still significantly improve the model quality. Sparsely gated neural nets, such as mixture of experts, is very practical and is cost-effective to build giant models. Finally, simple abstractions are critical to enable researchers and engineers to develop giant models together. You can find our tech report on arXiv and code on GitHub. Thank you.
Great, thank you, Shifeng. We have a number of questions, so we'll start with those. The first question is from Cliff Young, and he's wondering how are today's systems that we've seen reviewed today, such as GPU pods, TPU pods, Cerebrus machine, and others, how do they work with a G-shard approach? Does mixture of experts lead to load imbalance across different workers? And how do the systems deal with it, and what kind of solutions would you be looking forward to improve G-sharp performance on scale-out systems?
Hi. So the question is more about G-sharp approach. Can it work on other non-TPU platform? I would think so, because most of the technique is in the in-layer shardings. So those, as long as those support in the compiler level is ported to other platform, I think the algorithm will just work. As for whether mixture expert approach incurs load balance issues, I would say yes. But in our reports, and including original norms, original MOE papers, there's several algorithms that can help with that issues, especially during training. Because at this larger scales, you always have lots of training data, and then the key is making a very giant batch, so that when you do training, you can have lots of tokens to route to every expert. So you try to balance the loads.
Okay, so maybe I'll ask a follow-up question myself. So I'm curious, when you train these large models, what fraction of mixture of experts' weights are updated with each mini batch?
So during our training, for example, the largest setup, we use 2,000 experts, and the whole pod has 2,000 cores. So, and then the effective batch size is 1 million tokens or 4 million tokens. So, which that means during each training step, you almost always update all the weights.
Okay. Then we have a question from Yurong Cheng. So he's wondering how much node interconnect topology affects G-sharp performance. So some machines like TPU pods have direct links across nodes, and other machines require on network. So he's wondering whether that affects G-sharp performance.
So I think the one as I talked in the slide, there's one very obvious bottleneck is the all-to-all communications. On the TPU pod, because we have a mesh network, the latency increase as we scale up, or adding more and more devices increases a square root of the number of devices you add. I imagine that if you take exactly the model on the network, you some network will perform worse in that aspect. But there's other ways to deal with it because instead of doing O2L routing, you can have hierarchical or random sampling. So if working together with the algorithm designers, I think you will always have come up with reasonable ways to leverage the network topology to train models.
Okay. Thank you, Xinfeng. I think we're out of time of the session, so please everyone join me in thanking our speaker and actually all the previous speakers as well.
Thank you.
And with that, I think we will wrap up the deep learning scalar training tutorial, and the next tutorial will be on the quantum computing. Thanks everyone for attending.